All right. Welcome everyone to the ICANX talks this week. I am the moderator of this week. My name is Chao Zuo. I'm a Gila Associate Fellow and Assistant Professor at the University of Colorado Boulder. So this week in ICANX talk, we'll have the honor to present the final campaign for the Rising Stars of Light for the year of 2022. Rising Stars of Light is a worldwide campaign for young scientists in optics. The event was initiated by the journal Light Science and Applications in 2018 and co-hosted by ICANX since 2020. On Friday last week, we have enjoyed the final campaign for the PhD candidate track for the 2022 Rising Stars of Light. And this week, we are about to witness the final campaign for the faculty and postdoc track, as well as the final awards ceremony of both tracks. We're really excited about that. Before we start, let me first introduce the committee members for the faculty and postdoc track for the 2022 Rising Stars of Light. So the Andrea Lu, Albert Pullman, Lan Yang, Yidong Ostrang, Ming Chiu, and Dragomir Neshev. I should first say that unfortunately, Professor Andrea Lu cannot join us for the full session today due to a conflict of schedules. However, we do have Albert Pullman joining us today to make the 5-member committee. Professor Andrea Lu, maybe you can, before you leave for the session, perhaps you can share a few words with us about the event or what you want to say to the finalists today.
Sure. Thank you. Thanks for having me. It's a great pleasure to be here, and I've been involved with this event for a few years now. And I'm really honored also to be here today. I've been having a lot of fun to celebrate the great scientists that are doing amazing research on optics, on photonics. And also today I will try to stick around to hear some of the talks. Every year the event has an amazing lineup, and also this year it's very impressive. And I wish good luck to all the candidates. I was involved in the selection process, and it was a tough decision to select the finalists. We had an amazing line of applicants as every year. This year, I mean, every year gets even better. And the ones that are going to present today are fantastic, are already really stars in photonics. And I look forward to the event and to hear who is going to win. Thank you, everyone, and good to see you. Good luck.
Thank you so much, Andrea, and thank you again for spending so much time doing the pre-selection, which lead to the 6 finalists today. And also, I would like to thank all the committee members for doing that work. So as Andrea mentioned, there is a large number of candidates at the beginning, and out of all of them, we have selected 6 of them as a finalist today. Each of the candidates will give a 15 minutes presentation followed by 8-minute Q&A sessions. And after that, all the committee members will again give gradings to their presentations. And based on that, we will select the final winners for the 2022 Rising Stars of Light. So let me briefly introduce all the candidates today. They are Professor Wei Bao from University of Nebraska Lincoln. Professor Lin Chang from Assistant Professor from Peking University. Qiushi Guo, a postdoc at Caltech, and he is also an incoming Assistant Professor at the City University of New York. Jariwala, Assistant Professor at University of Pennsylvania. Yating Wan, Assistant Professor at King Abdullah University of Science and Technology, and Chao Zuo, Professor at Nanjing University of Science and Technology. So without further ado, let's start our first presentation today by Lin Chang from Peking University, and he's going to talk about heterogeneous integrated photonics. Lin, please take your time.
Can you see the screen now?
Yes, everything is good. I can hear you. I can see your screen.
Yeah, great, thanks. Hello, everyone. Thanks for watching this event. And my name is Lin Chang. I'm an assistant professor in Peking University. Today, I'm going to talk about an important trend in silicon photonics, which I believe will, in the future, change the information technologies. And so first, some brief introduction of the background. So as we know, over the last decade, silicon photonics has become a very hot topic in both industry and academia. And the big hope for silicon photonics is to miniaturize a wide range of optical systems in a high volume and low cost way due to the usage of large silicon wafer and the mature electronic CMOS process. However, this packs a great promise. So if you check the current status of silicon photonics, you might feel a bit disappointed. And this is a very famous report from Euler for the nowadays silicon photonics market by applications. And the yellow and the green circles are the technologies related to the communication. And you can tell that now the communication area is still dominating the silicon photonics market. And the result is that the whole scope of silicon photonics now is still quite small, especially compared with the electronics. And so where's the problem? So the problem comes from the difference between the electronics and the photonics. So as we know, in electronics, silicon can provide most of the functionalities by itself. However, for photonics, it requires that multiple materials to be integrated, so because they can provide a lot of functions that silicon couldn't really do. For example, like the gain, electro-optic effect, nonlinear process, low loss, and the non-reciprocities. And actually integrate those materials onto silicon is a quite a challenging job. So far, only very few institutions can do this. Like Intel can integrate the indium phosphide onto silicon with high quality. And there's also some like foundries can integrate the silicon nitride. However, once silicon nitride gets integrated with SOI, due to the compatibility problem, they couldn't really deliver the low loss as they should have. So indeed, most of the silicon photonics platform nowadays we are talking about is based on pure SOI. So the material integration actually is really the bottleneck for silicon photonics. So my job has really been focusing on develop advanced heterogeneous integration technology and to try to bring more materials onto silicon platforms. So here I will mainly focusing on two material systems. So the lithium niobate, the gas L-gas, and the silicon nitride. And all the process and the platform I'm going to discuss today are based on wafer scale process so that they are compatible with high volume productions. So first, the first material I worked with was the lithium niobate. And this material is desirable because it's large electro-optic and second order nonlinearities, which silicon doesn't really have. And in 2016, we demonstrated the wafer level thin film lithium niobate process. At that time, a really big challenge for this material platform on integrated photonics is how to harness the second order nonlinear effect. Because previously in bulk optics, this was done by the periodically pooling of the bulk crystal. However, at that time, there was not this kind of technology cannot be directly transferred onto the thin film on silicon. So I developed a special technology called the surface pooling, and which can like periodically flip the domain within submicron scale for thin lithium niobate. And then using this technology, we developed the first thin film pipeline and achieved efficient second harmonic generation on chip. And this technology then has been widely applied, and nowadays if you check the nonlinear based lithium niobate device, you can find that most of them actually use these kind of technologies. So, but after demonstrating this platform, we started to realize that for many applications, actually we do need a much higher nonlinear conversion efficiency and a better compatibility between laser and the nonlinear device. So we started to develop another material platform, which is the gas-on-gas on silicon. And this platform is done by the heterogeneous integrated like high quality L-gas or gas film onto oxide silicon substrate. And however, the problem for this platform at the beginning is that as we know, all those 3 files previously were notorious for their high loss. So we really spent a lot of effort to try to develop a low loss process, including the surface passivation, as well as the optimized lithography. And then by combining those strategies, we finally achieved the the lowest loss 3 5 waveguides with quality factor beyond 3.5 million. And such value, if not lower than still other silicon, is definitely like one of the best semiconductor waveguide we can get. And then combine those low loss with the giant nonlinearities this platform has, we achieve the most efficient second and third order nonlinear process on chip. At a microwatt scale, we can get like a significantly frequency converted into the second harmonic wave, as well as the parametric oscillation for microcomb generations. But if you want to really like push the limit of low loss, maybe silicon nitride is a better platform. This material has been widely used previously as the low loss material, and they can achieve with you like the best a few dB per meter. And we further push this limit and make the loss below like 0.1 dB per meter by introducing a novel waveguide structure and advanced fabrication technologies. And then we combine with, we collaborate with photonic foundries and achieve like an 8-inch low loss silicon nitride platform. And on this platform, we achieve like more than 260 million quality factor, which is a record among the integrated photonics and with very high yield over the entire wafer. And then with those like great properties of the individual device, we try to like apply different integration technology and combine them onto the same substrate. And here we show 3 different platforms we did and try to combine different materials together, including the integration between lithium niobate and silicon nitride, and also some active 3 5 materials with low loss passives. And those kind of platforms are suitable for fully integrated photonic integrated circuit. And then moving forward with those desirable properties on the heterogeneous silicon platform, we try to explore the device level demonstrations. And here I will mainly focus on the integrated light source, because this is the key in almost all the integrated photonic platforms. So as we know previously, for the integrated light source on chip, they are usually based on semiconductor lasers with pure 3 fives. And suffer from the material property, they usually have relatively low coherency and tunabilities. And the strategy we use here is try to bring high Q resonators together with semiconductor lasers. And then by combining them together, we can achieve a bunch of desirable properties, which previously didn't exist in semiconductor photonics world. And like the narrow linewidth, the multi-channel light source, which is the microcombs in our work, the frequency modulation of the laser, as well as the isolation capabilities. So the key of this demonstration is to find a way to like bridge the 3 5 laser with the high Q resonator. And one new mechanism we developed is the self-injection locking, which is to leverage the backscattering of the high Q resonator and to collapse the lasing state of the 3 5 lasers. And by doing that, we can get a significantly reduction of the noise. Here is showing some like results. And the injection locked laser compared to free running semiconductor laser get more than 50 dB noise suppression ratio. And this brings the semiconductor laser into a new regime of the coherency on integrated photonics. What we achieve is 60 millihertz line width, and it doesn't even have a counterpart in the commercial fiber laser. And previously, if you want to find the high coherence laser like this, you need to go to some really high precision measurement system and use a very large tube to build the ultra high Q resonators and lock the laser onto it. And another demonstration we achieve using the injection locking is the integrated microcomb generation. So it plays a key role here because the self-injection locking can enable the locking of the operation wavelength of the laser stay at a certain detuning to the resonance of the cavities, which is necessary to generate a coherent microcomb state. However, this previously requires a bunch of very complicated control and feedback circuitries. And here, by doing the self-injection locking, all this can ultimately happen without any electronics. And actually, once you turn on the laser, you can generate the coherent microcomb state. By using these strategies, we generate several important microcomb, including the tachycurve comb as well as the microwave combs. Those kind of combs actually are quite important for optical metrology, I will discuss later. And another important function previously missing in integrated photonics world is the fast frequency modulation capability. This is essential for FMCW LiDAR. And here, the strategy we use is to combine the lithium nail-based external cavity with 3.5 laser, and which create a new kind of laser. We call it a POCOS laser. This kind of laser can get a really fast tuning capability while maintaining the wide wavelength tuning range and the narrow linewidth. We can also harnessing the large nonlinearities on this platform and get the dual wavelength lasing. This is the first dual wavelength laser for integrated photonics. And although all of the properties I mentioned before are very important for photonics, but without isolators, they couldn't be really useful. And we also demonstrate the first integrated isolator with lasers together in integrated photonics by using the nonlinear isolator. And the strategy we use here is to take advantage of the Kerr effect, and so that we can achieve the isolation within the operation power of the DFB laser. You can tell from here, once the laser is turned on, the reflection gets significantly suppressed. And this kind of approach doesn't require any magnetic field or the spatial temporal modulation as required before. So with these advanced devices, we use them to extend the scope of silicon photonics for many new applications. And one example we do is the time frequency metrology system. And here, what we demonstrate is the optical frequency synthesizer based on integrated photonics by combining the narrow linewidth laser, the microcomb generator, and the efficient nonlinear devices. And by doing that, we bridge the gap between electronic frequency and the optical frequency so that we can use electronics to arbitrarily generate very precise frequency over the entire C-band with Hertz level accuracies. This corresponds to 10 to the minus 15 accuracy, and such kind of accuracy has never existed before in the entire semiconductor chips, including both electronics and photonics. So actually, this is a really good example to show how the heterogeneous photonics platform can potentially change many applications. As you know, 40 years ago at NIST, the most precise time frequency system takes the whole room space. And 20 years ago, due to the invention of microcombs, the frequency combs by modular laser, they shrink the system onto the tabletop scale. And last year, due to our integrated platform, we can now combine all the components of the system onto a package, which is a small matchbox, in significant reduction in SWAPC. So, and then another application, probably more closer to their daily life, is the communication. And here we use the microcombs to drive the silicon photonics system to make it very massively parallel. And then by increasing the channel, we achieve the world record data rate transition for optical transceiver, as well as a reconfigurable microwave filter, which can be used for 5G or 6G applications. And with this, I would like to conclude my talk. Actually, as you know, 20 years ago, the first generation of photonics is based on pure 3.5, and they are suitable for a communication experiment. And over the last 10 years, silicon photonics is really the game changer. And then it can extend the scope of the application and provide the possibility for some other applications. And I believe with the heterogeneous integration we demonstrated here, we can not only improve the integration level and the performance of the previous demonstration, more importantly, we can really extend the scope of the information technology by providing on-chip photonic solutions. So with this, and I would like to conclude my talk, and also in the end, I would like to acknowledge all my colleagues in Bauer's group, as well as all my group members now at the Peking University, and all my collaborators previously worked together with us. Thank you very much, and I would like to take any questions.
Thank you, Lin, for your very nice talk. Are there any questions from the committee members? So please, yeah, Albert.
Yeah, hi Lin, this is Albert Polman here from Amolf in Amsterdam. Thanks very much, very fascinating talk. And of course, the history of silicon photonics is very old, but what we see here is totally new applications, all integrated in a very small area. And I think that's very, very impressive.
Thank you.
I had a question about the losses in your waveguides, because in the end, they determine many of your functionalities. So in gallium arsenide, there was a fundamental limit in the loss. And I'm curious what you think are the fundamental loss mechanisms there and how they can be maybe partly avoided.
Yeah, that's a really good question. Actually, for the gas and L-gas system, we believe that the highest Q we can achieve is probably at the level of the 10 million or 20 million based on the current growth technology. And the reason we see that is because actually we have a collaborator who did a lot of high Q mirror by doing those using those L-gas and gas crystals. And then they measure the material loss of those high Q cavities, and they can extract the loss caused by the absorption. So which actually is caused by the MOCVD or the MB growth. And we believe that for the current growth technology, the limit is probably around 10 to 20 million. But on the other hand, I think with only 3 million Q on chip, this already leads to a very efficient frequency conversion. And I believe that if we can further improve the fabrication as well as the material growth technology, I think this platform can really be very powerful in the nonlinear process as well as some other applications. Yeah.
Great. Okay. Thanks for the answer. Very clear. Thanks very much.
Thank you.
All right. Any other questions? Yeah, Professor Dragomir Neshev.
Hi, Lin. Very impressive talk. Dragomir Neshev here from the Australian National University. So I just wanted to hear your vision about integration of magneto-optic materials with silicon, because probably for true isolators, you need something like this. Can you share your vision on this?
Right. Indeed, if you want to build a power-independent isolator, that's probably the best way to go. So I think at this point, there are several strategies to integrate YAG on chip. Heterogeneous integration is one, and also there are some direct deposition for the monolithic integration. So I think one of the challenges for YAG is that it is relatively lossy. And the loss actually at this point is significantly higher compared to state-of-the-art or SOI or silicon nitride waveguide. So this potentially can be a problem if you want to build a very complex photonic integrated circuit. You might need many isolators there. And also, I think if you want to do either heterogeneous integration or the monolithic integration, the process itself at this point still have some compatibility problems. Usually the foundry don't want to do that. So it's still a very tough material to deal with at this point. So for our first demonstration of the directly integrated isolator with laser, we choose to use a nonlinear effect. But indeed, for some more strict requirement or power independent application in the future, we might spend more effort trying to develop those YAG or other magnetic materials. Yep.
Thank you so much.
Thank you.
All right, Professor Ming Chu.
Yes, very impressive work. I have a question about the alignment accuracy. So for the heterogeneous integrations, you need to integrate several materials together. For example, you need to align your lasers with your devices waveguides. So what is the accuracy of the alignment and how important and what kind of technology you are using?
Yeah, that's a really good question. Yep. Thanks. That's a really good question. Actually, that is indeed one of the advantage of heterogeneous integration, because all the lasers actually we did here is processed after we finish the bonding. So actually the alignment is done by the lithography, basically the stepper itself. So we can achieve like more than like within like a 100 nanometer alignment accuracy. There are some also other technologies for the integrate, for example, the transfer printing, which you like made the laser first and then try to integrate with your passive components. That one, you probably need a really careful job on your alignment. So, but here, all we do is directly wafer bonding and then do our fabrications later. So we usually don't worry about the alignment by itself. Yeah.
Okay, thank you.
All right. Any other questions? Professor Lan Yang. Sorry, you are muted.
Thanks, Professor Lin Chang, you've given a wonderful talk. I think you already answered some of my question. So you talk about the challenges for those heterogeneous integrations, such as alignment, loss, and compatibility, right?
Yeah.
And what's in your view is the biggest challenges in integrating different materials medium in one wafer?
So I would say it's the compatibility. So the challenge is that how to integrate many materials together while maintaining their desirable properties. For example, it's a very tough job to like still maintain the low loss of silicon nitride while you put those 3.5 onto it. So actually for that, we develop a lot of special technologies, try to protect the silicon nitride layer and avoid the degradation of the performance of the nitride waveguide itself. So, and with more and more material get integrated, the compatibility problem might be an even bigger challenge, particularly if you consider that Intel developed the indium phosphide on silicon process almost like more than 10 years ago, but it took them almost in the entire 10 years to get this like to be commercialized and now they can deliver the millions of transceivers every year. So it definitely took time, but I think our job is to try to like first do some proof of concept demonstration for the wafer level and to show the possibility. And then I think the large foundries will take over them and try to further improve the yield and yeah, things like that. So.
Okay, then I think you're in the best position to tell us the difference between heterogeneous versus hybrid integration, because for hybrid integration, you don't involve this compatibility issue, right?
Right. So I think nowadays we usually, I mean, people might have different definitions, but nowadays, at least in our group, we define hybrid as the packaging, basically the chip-to-chip like butt coupling, something like that. And for heterogeneous, we usually define as at least like we do the wafer bonding and then further do the processing. We call those as heterogeneous. But I completely understand like different people might have different opinion. Or their own definition on this. So yeah.
Okay, great. Thanks a lot.
Thank you.
All right, very nice. Thank you, Lin, again for your very nice presentation. Unfortunately, we cannot continue with the Q&A sessions due to the time limit, but thanks again.
Thank you very much. Yep.
All right, so our next speaker is Professor Deep Jariwala from University of Pennsylvania. Deep, please take on the stage.
Okay, can you see my screen okay? Let's see.
Yeah, except that it's not in presentation mode. Yeah, now it's good.
All right, perfect. Well, thank you, Shuo, for the kind introduction and for the judges and the committee and the organizers for giving me this opportunity. So my talk will be more on the fundamental side and talking about strong light matter interactions in very, very thin semiconductors. Here we call them as atomically thin semiconductors. So let me get started and jump right into the matter. So when we talk about very small scale or low dimensional semiconductors, excitons are the ones that dominate optical properties of these semiconductors. And there is a wide range of materials that demonstrate optical properties, and therefore there is also a wide range of low-dimensional semiconductors. Of course, this is not new. This has been known since a very long time, especially looking at optical properties of excitonic semiconductors started long back in 3-5 quantum wells and quantum dots. Some of these materials were also discussed in the previous talk. But then as time evolved, newer and newer molecular or low-dimensional materials were discovered, wherein very strong excitonic responses were found to be extremely stable at room temperature. And these were, first of all, organic small molecules and polymers, which have been commercialized into OLEDs and other types of optoelectronic devices. Colloidal nanocrystals also came along, and then finally even carbon nanotubes, which are one-dimensional forms of graphene, if you will. And the last ones I would say are these two-dimensional materials, namely two-dimensional transition metal chalcogenides and also some halide perovskites. I should mention that our group works on various types of excitonic materials. The three highlighted in the boxes over here are the ones we predominantly work on. But today, due to lack of time, I'm going to be focusing mostly on results of transition metal chalcogenides and a little bit of results on the halide perovskites. If need be, I can talk about carbon nanotubes later if time permits. Okay, so let me jump in and outline or mention why we are interested in studying excitons in 2D transition metal dichalcogenides, or why are these materials important in the first place. And so if you look at or try to compare semiconductors as a whole from the perspective of their optical properties, which is band gap versus absorption coefficient, these transition metal dichalcogenides, which are essentially layered compounds, with a very weak out of plane, but very strong in plane bonding, they have band gaps in the visible part of spectrum. In fact, for some of these bulk materials, the band gaps are actually very close to the Shockley-Quezier limit, right? And the more interesting thing about them, and at the time when we were looking at them from absorption device properties, we found that their absorption coefficients are some of the highest known, about 10 times more than gallium arsenide, 100 times more than silicon. So clearly, they are some of the most absorptive materials we have seen, even more than organics. But the other thing that as you start digging further into the literature and that you find is that these materials also confine light extremely well. So here, what I'm showing you is our optical constants of bulk WST. Okay, now you would expect that typically in bulk cases, like you have in 3-5s, excitons don't dominate the optical response. But because the bonding structure is so anisotropic, they retain a fair degree of quantum confinement, even in the bulk case. By bulk, I mean multi-layers. And you can see that the optical dielectric function is still highly wavy or dominated by excitons over here. But the other interesting thing that you also observe is that even sub-gap, where actually the imaginary part of the dielectric function, or K, is approximately 0, the refractive index is extremely high. It's more than 4. So not only they are highly absorptive materials, they can also confine light extremely well due to the high refractive index sub-gap. And many people have also alluded to them as for use in photonic devices as waveguides and so on, though I would say they are still pretty early on in the research stage. Okay, so why were we interested in them? We are interested in them because not only their properties are dictated by excitons, but these excitons are also tunable. How are they tunable? Well, they could be passively tunable as a function of structure, right? So as you go from monolayer to multi-layers, the amount of oscillator strength that is there in the exciton, amount of binding energy that is there in the exciton varies a little bit, right? So that is one way to tune them. But the other way to tune them is actually, in the case of monolayers in particular, they are very much amenable to putting down electrodes. And once you put down electrodes and gate them just like you would gate any semiconductor in a transistor, you can move the Fermi level, and then you can change the optical constants by a very large magnitude, right? I'm sure the people in the silicon photonics and other 3-5 communities know how difficult it is to get large electro-optic effects. Here we are showing that by as a function of applying voltage or electric field, you can tune the indices by up to 40%. That is a very large value as compared to most other materials that we know of in the visible part of spectrum, right? So that is a clearly advantageous and also interesting to study other fundamental phenomena. Okay, So why we were interested in looking at excitons and particularly combining excitons with photons trapped in cavity media is because if you look about 30 years ago, all of the research in this field was dictated by epitaxially grown 3-5 materials, such as 3-5 quantum wells, which was sandwiched again in epitaxially grown Bragg mirrors, right? And so this was basically the state of the field where the quantum wells used to host excitons, and then these photons that were trapped by Bragg mirrors used to would lead to strong light matter coupling, leading to formation of Exciton-polaritons. What has happened in the past 10 years or so is with the advent of these van der Waals materials, the field has been democratized. In other words, anyone who can get access to a crystal can scotch tape or exfoliate a small piece of van der Waals quantum well, which is also excitonic, stable at room temperature, put it onto arbitrary substrates. What this has enabled people to do is combine different types of optical cavities, which were very difficult to integrate with these epitaxially grown quantum bells, namely plasmonic cavities or other photonic crystal cavities, and so on. As a result, there has been a large explosion in results in this area. I'm not listing all of the groups over here, but we have tried our best to summarize all of them in this review paper. But people have been able to see very large Rabi splittings of more than 100 MeV or even a couple hundred MeV at room temperature. This opens up new possibilities to form these long heralded, both are achieving Bose-Einstein condensation of polaritons and also polariton lasers from them at room temperature, though that has not yet been achieved. And I should mention that the active research is going on in this area by many groups. Okay, so keeping all these interesting and exciting optical properties in mind, our goal was to see how can we trap light in these materials very effectively. And certainly you can use high-Q optical cavities, but the fact that the optical constants of these materials themselves are so high, we took the approach of trapping light or self-trapping light within them. So one way to do this, which was actually not very hard to figure out, is if you take even very thin layers of these materials, and if you have them freestanding, you would see that most of the light will go through them. Or if you make them quite thick, most of the light will get reflected because of the refractive index mismatch. But if you place them on reflective materials such as gold or silver, you will have propagation losses and large propagation losses as light goes through it. And by the time it comes back up with the next incoming ray, there would have been enough phase shift, again, due to large index and large absorption, that you could have destructive interference over here, leading to near perfect absorption. Okay. Again, I should mention over here that this thickness is not lambda over 4n. It's actually deep sub wavelength in the range of 10 nanometers or so. Okay, so this is not like the classic Fabry-Perot. It's more like a lossy Fabry-Perot, if you will. So keeping this effect in mind, we wanted to explore if you can actually couple photons very strongly with excitons in this media. So we did these experiments where we varied the thickness of tungsten disulfide. Tungsten disulfide is the choice material over here because it has a very nice exciton over here at about 2 eV or so. And as you can see, for larger thicknesses, you can have this very nice exciton dip in reflectance. But as you go below some critical thickness of 15 nanometer or so, these peaks split into upper polaritons and lower exciton-polaritons. You can see these extremely well in experiments too, where the peaks are very nicely split. You can take the experimental values, superimpose them on the simulations or even a two-coupled oscillator model, and you can see it lines up really, really well. So this was great. You could achieve this at room temperature under ambient condition without the need of external optical cavities. All you are doing is taking very thin materials, placing them on reflective substrates, achieving even near unity absorption in the process. As you can see over here, the reflectance has dipped to 0. You can do this even for higher order modes. If you keep increasing the thickness, you can see this keeps going and you can get more and more amounts of splitting. You cannot observe this, however, on 3.5 and 2.6 semiconductors for a very specific reason. The oscillator strength in the optical dielectric functions must be focused into the excitons. If it is not focused into the excitons, this kind of strong light matter coupling that we get in these transition metal dichalcogenides or all excitonic semiconductors for that matter with high index or real part of index, you won't see it for similar band gap semiconductors which do not host excitons or do not have oscillator strength focused in excitons. Okay. So having proven all this, we wanted to see if we can push the limit on this and actually go to monolayers. Why do we care about monolayers? We do care about monolayers because when we go to monolayers, you do get a direct to indirect to direct band gap transition. and you actually get much larger emission efficiency coming out of your material now. So that is great. The problem is trapping light in monolayers is even harder. Why? Because the semiconductor is less than 1 nanometer in thickness. This is 0.7 nanometers, extremely hard to trap light. So we started debating over this. How can we trap light in these very thin semiconductors without making high Q or very expensive optical cavities? Again, we want to utilize the intrinsic optical property of the material to confine light in them. So we had postulated a few ways of doing this, but none of them actually gets you very high absorption. It gets like 40% or so, and none of them really work after that. So when we started debating this with our students, we found that the one way to do this would be to maintain multi-layer structure, but monolayer optical and electronic properties. And the way to do this was to separate out individual layers of these crystals with spacers that are thick enough that will prevent any overlap of the wave function of electrons or excitons in these two layers, retaining monolayer optical and electronic properties. Okay, so we first went ahead and did a simple transfer matrix simulations again to figure out what would be the best space and thickness. We found about 3 nanometers or so should work. And if you were to then artificially create this multi-quantum well or super lattice structure, you would see that even for thicknesses or number of unit cells, and these are each bilayer over here is a unit cell, for about 6 or 7 unit cells, you can get nearly 100% absorption. Again, I want to emphasize there is no external optical cavity over here. What really happens is that because of large refractive index mismatches, as the light comes in, it keeps bouncing in between the layers and gets nearly completely trapped. I then thought that let's go and make these kind of layers. Now, those of you who work with Scotch tape materials, you would know that as you start stacking more and more materials, the overlapping area almost reduces to sub-micron levels, and it becomes a practically useless material. This is why we went on to materials growth approach. And I think this is where most of the innovation now lies. You can actually grow these materials over large areas, over wafer scales, not only the excitonic semiconductors in monolayer form, but also hexagonal boron nitride, which is another very interesting optical material with control thicknesses of about 3 nanometers and even below. This is the reason why I have been emphasizing that these two-dimensional materials are no longer limited to tiny Scotch tape crystals in the lab. They have been made into not only 2 to 4 inch wafers, but also 8-inch wafers by companies such as Exciton. People have started putting them into foundries, so they are getting serious. Okay, after 10 years of research, 10, 12 years of research, they are truly getting serious in terms of scalability. So we took some of this grown material and actually stacked over centimeter scale multiple layers, okay, with hand. This is all transfer process, so it's all manual, but you can automate it to make this kind of artificially made van der Waals super lattice. And in these structures, you can actually see very nice quantum well-like separation. If in fact, with increasing number of n, you can see much larger and larger absorption approaching near unity levels over here in the exciton. But most interestingly, when you shine light at them at an angle, once again, this multi-layer structure traps the light into a waveguide mode, which ultimately couples to the exciton and splits into exciton-polaritons beyond a certain angle or incoming wave vector of coupling. Again, I should emphasize this is all at centimeter scale, room temperature, ambient conditions, normally seen only at cryogenic temperatures in other systems. We have done the similar things with naturally occurring quantum wells. These are the famous halide perovskite materials. If you look at halide perovskite materials, it's difficult to produce them with high phase purity. We have been able to do this with our collaborators at Rice University and have measured their optical dielectric function, which are again very strongly excitonic. And we have been able to also show very strong light trapping in them, including formation of emission of polaritons at room temperature. And you can get emissive polaritons from them because 1, they are highly emissive, but 2, they are naturally direct band gap at room temperature. So I'm coming to the end, and what I would like to say is the next phase of all of this research is actually achieve active tunability. And you can get active tunability by again applying electric fields to them, and we are having some preliminary results in this regard. So you can take these quantum well-like structures and apply electric fields or gate voltage to them and tune the phase of incoming light, as well as use magnetic fields, because many of these two-dimensional materials also have magnetic properties, and the spin alignment also produces very interesting linear dichroism and other effects, which we are trying to tune now as a function of magnetic field and also strain. So with that, I would like to end and say that layered two-dimensional semiconductors have very interesting properties that make them quite exciting for both classical and quantum photonics. But the key advantage or innovation required is actually scaling up their growth and manufacturing, which is really important. And people should find new ways for actively tuning the optical properties, such as magnetic field strain and so on. And of course, all of this work is done by the hardworking students and postdocs, and thanks to all of the funders who fund us too. And there is a large number of collaborators involved, again, all over the world. Thank you all for your attention. Again, I'm happy to take any questions.
Thank you very much, Deep. Are there any questions from the committee? Yes, Edwin.
Thank you. This is really exciting research. So I had a question regarding those alternating monolayer systems. So can you tell us more about what is the coupling efficiency from an external source or an integrated source? So how do you see building devices and what kind of efficiencies you will have with integrated devices out of these materials, and what kind of losses, coupling efficiencies you're targeting, you're having?
Right. So a great question. When you have very thin materials, coupling efficiencies are going to be an issue. One of the ways we have so far, because these are fundamental studies, we are just shining light at an angle. But we have done simulations where you could make a grating structure on the side, and you can use the grating structure to couple light into these layers. And in these simulations, we still get the same grating coupler efficiencies as you would get in silicon photonics, right? Because if you look at multi-layers of these materials, their refractive indexes are large enough. So you can make thin enough and thin enough grating couplers that can also couple light into them with the same efficiency as you would get in silicon photonics typically. Yeah, but to your other question, if you're thinking about losses, if you want to use them sub-gap, the materials are still not mature enough for like a lossless application, because again, the sub-gap loss is still significantly high compared to, say, silicon nitride or silicon or 3,5 materials. And I think that is where most of the innovation has to be if you want to really use them or for a integrated application, as you pointed out.
Okay. Thank you.
All right. Other questions? Yes, Albert.
Yeah, hello, Deep. A very impressive talk. Thanks very much. It's also amazing you can put all these multiple layers on top of each other and make really reproducible structures, it looks like. And I had very similar questions as the previous one, but just as a clarification, I thought you said in the talk that you were coupling to waveguide modes, even though you didn't have any grating coupler structure. Did I misunderstand that, or do you have other means to couple?
No, you did not misunderstand. When we were coupling to waveguide modes, because we were shining light at an angle.
Mm-hmm.
Right. So as we were shining light at an angle, they were getting coupled into the and this was only along one polarization that you would generate the waveguide modes. You would not generate it along the other polarization.
Okay, thanks.
But if I understand, as a follow-up on the same thing, that's not your preferred way of integrating, because it's a less controlled and less efficient means as opposed to the gratings.
Yes, yeah. Certainly.
Just for basic research.
Yes, this is basic research. Yes.
Mm-hmm.
Other questions? Yes, Professor Lan Yang.
It's a wonderful talk. Thanks a lot for the education about 2D materials, which have a lot of application. One question is about your innovation about the growth of large-scale monotonically growth of these 2D materials. I can understand that you can grow thin layer, but how to grow multi-different layer? Is that also applicable to multi-layer?
Yeah. So actually, this is a great question. And, if I had more time, I would have emphasized on it more. I've been telling the community that one way to actually take these materials even forward is to grow multi-layers. Because if you grow multi-layers, then you have thick enough medium with high index that you can really do some nice waveguiding or confining of light with it. The issue is the following. Because they are van der Waals bonded, actually, if you try to grow the second layer on top of the first layer, maybe it grows okay. But as you go third, fourth, fifth layer, the nucleation sites become random and they start going out of plane. So this is, from a materials perspective, one of the big standing challenges. How do you grow high optical and electronic quality, but thick? By thick, I mean 10, 20, 30 nanometer layers. So far, there has not been much work in this area. We have unpublished data. I'm happy to send them to you later on. It's still, we haven't even written a paper where we have managed to make single crystal-like optical quality, which means by comparing optical constant, but in wafer scale thin films, which are 50 to 70 nanometers in thickness. So we have achieved this in the lab. And the way to do it is actually not by molecular scale precursors, but actually starting with the metal and sulfurizing it over a long period of time on an epitaxial substrate.
Wonderful, thanks. That's impressive.
So quick follow-up questions on the girls. How do you compare the qualities, either optical qualities or electron mobilities of these girls grown 2D materials with the traditional approach based on exfoliation?
Again, great question. I think, if you want to compare this quality, it really depends on the application. If your application is electronic devices, where actually a large focus of research also is on these materials, you want to compare the mobility, right? The field effect mobility or Hall mobility would be the best way to compare them. But if you want to compare optical quality, one would be the magnitude of optical dielectric constants. But most importantly, if you want to use them for a waveguiding application, it would be sub-gap optical constants. So those would be the two way to, it's a sub-gap imaginary part of optical constant, sub-gap absorption.
All right. Are there any other questions from the committee? Oh yeah, Albert, maybe one last question. Yeah.
Maybe just a short one. In the beginning, you mentioned this electrical gating and charge injection to change the optical properties. Do you see any effect on the exciton line width as you inject charges in there?
Yeah, indeed, I do. Yeah. So the exciton line width actually broadens, because what happens is as you gate it, you inject more either electrons or holes, depending on which direction you are gating. And so because of the large quantum confinement, these TMDs also have a very interesting property that they form charged excitons. So trions, right? Or 2 electrons, 1 hole, or 2 hole, 1 electrons. And these are basically second particles. So a new oscillator has come into the picture now. And so now these 2 oscillators are basically, close to each other. So you sort of get a, double hump peak sort of. Yeah. So
Okay.
that leads to broadening of the light width.
Yeah, great. Thank you.
All right, great. Let's thank you again for Deep for your very nice presentation. And for the sake of time, we need to move on. Our next speaker is Professor Chao Zuo from Nanjing University of Science and Technology. Chao, the stage is yours. And I think you remain muted.
Yeah, so can everybody hear me and see my screen?
Yeah.
Now?
Yeah.
Okay, good. Thanks, Professor Sun, for the kind introduction. Hello, everyone. My name is Chao from Nanjing University of Science and Technology. It's my great pleasure to have this opportunity to give a presentation here. Today, I'd like to talk about computational quantitative phase imaging. My research group, SCI Lab, here is our website, is dedicated to the development of novel computational imaging technologies with a focusing on computational phase imaging and metrology. In mathematics and physics, the term phase specifies the location or fraction of a particular point with a wave circle of a periodic function. In wave optics, the phase is a key component for characterizing the electromagnetic wave, running into a unique tool for label-free microscopy. In geometric optics, the phase can be used to establish unique correspondence between 2 stereo fringe patterns and utilize optical triangulation for 3D optical metrology. In statistic optics, the phase is indispensable for correlation imaging of an incurrent object field based on the Vansic-Zenick theorem. In all these 3 cases, we can only record the light intensity directly, but the phase information is lost. Therefore, we have to use computational imaging techniques for the retrieval of the phase information. Consequently, computational phase imaging and metrology, including all these 3 aspects, is the main research area of my lab. In this talk, I will focus on the first case, that is quantitative phase imaging. The optical microscope, invented for more than 400 years ago, has now become an indispensable and ubiquitous instrument in many areas of science and technology. In particular, fluorescence microscopy has achieved several leaps from 2D wide field to 3D confocal, and then to super-resolution fluorescence microscopy, greatly promoting the development of modern life science. However, fluorescence microscopy suffers from phototoxicity, photobleaching, and cannot reveal the whole cell landscape. Therefore, it is particularly important to develop labor-free microscopy techniques. The electromagnetic wave can be characterized by a phasor or complex amplitude, having both amplitude and phase. Although most living cells and tissues are transparent, when light passes through them, the phase is delayed in proportion to the reflecting index and thickness of the cell. Therefore, quantitative phase imaging, QPI, is emerging as a powerful tool for label-free microscopy. I was so lucky to enter this field 10 years ago. When I read the book written by Professor Gabriel Papscu, I was so fortunate to know Gabi and so sad about his passing. He will always be remembered by us as a distinguished leader and inspiring mentor in biophotonics. The most well-established method for QPI is based on interferometry and holography. For example, in digital holography microscopy, by superimposing an additional reference beam, the invisible phase can be converted into the fringe pattern. After the fringe analysis, we can demodulate the phase from the fringe pattern. This technology has made remarkable progress and now has become one of the most classic QPI approaches. Nevertheless, the complex optical configurations and laser speckle noise severely limit their applications in optical microscopy. To alleviate these limitations, in recent years, many researchers have gradually turned their attention to low coherence interferometry. Notably, Gabi developed SLIM and WDPM. These white light methods eliminate the coherence noise and significantly enhance the system stability. On a different note, the above-mentioned issue can be more radically addressed if the QPI can be raised without resorting to the interferometry. These non-interferometrical techniques are known as phase retrieval, which utilize only intensive measurements under defocusing or asymmetrical illuminations. However, conventional phase retrieval approach are still based on coherent illumination assumptions. Two fundamental theoretical questions need to be answered for their broader applications in optical microscopy. What is the definition and physical meaning of phase for partially coherent fields? What is the quantitative relation between intensity and phase for partially coherent imaging? To answer these questions, we derived the generalized transporter intensity equation and gave a strict definition of phase, so-called generalized phase, for partially coherent field. We established the phase transfer function theory on the partially coherent illumination. The phase OTF is the imagery part of the complex OTF, which progressively vanished with the increase in the illumination NA, suggesting we cannot see phase object under a bright field microscope with incoherent illumination. To address this problem, we introduced illumination coherence engineering for phase OTF optimization. We found that the matched annular illumination not only provides a smooth response for both low and high frequencies, but extends the imaging resolution to the incoherent diffraction limits. By using high NA annular illumination, it is shown for the first time that TIE phase imaging can achieve a laser resolution up to 200 nanometer based on only 3 intensive measurements with slightly defocusing. We also demonstrate AI-TIE by long-term time-lapse imaging of HeLa cell mitosis. Our method removes any concerns about phototoxicity and photobleaching, allowing for quantified subcellular dynamics like the moving viscous and fluctuating laminopedia, and calculate the cell confidence ratio over an extended period of time, up to 16 hours. We also apply our AI-TIE to multimodal imaging of HeLa cell apoptosis. Based on the quantitative phase obtained, we can realize zenic phase contrast, DRC, in a fully computational way without resorting to any actual hardware. Okay, let's return back to the phase OTF. Besides defocusing, breaking the symmetry in the optical system is another way to produce phase contrast. The most represented method is called Fourier ptychographic microscopy, FPM, is a computational microscopy techniques for high-speed bandwidth product imaging by replacing the light source of a conventional microscope with a programmable LED array. By illuminating the sample from different angles, we capture intensity image with a low magnification object length. These low-resolution intensity images are synthesized in the Fourier domain to reconstruct a complex image, including both amplitude and phase, with both high resolution and very large field of view. The image resolution by IPM is determined by the sum of the objective NA and the illumination NA. In a conventional free space FPM setup with a LED array, due to the limited illumination angle, the final synthetic NA achievable is much smaller than 1, which is insufficient for high-resolution imaging applications. To solve this problem, we developed resolution-enhanced FPM by insert a programmable dense LED array into our immersion condenser. The illumination NA can be significantly enhanced from 0.5 to 1.2 for conventional free space FPM. So the synthetic NA is improved from 0.4 to 0.9. And the element 5 of group 10 of the USF target can be resolved. You can compare the results. By using REFPM, we can further extend the frequency support significantly from 0.4 to 1.6, so that almost all the elements in the target can be resolved. Consequently, we can achieve 300 nanometer imaging resolution by using only a 10x objective length. The final speed bandwidth product is 15 times higher than that of a conventional 16x microscope. With REFPM, we can observe 20,000 red blood cells simultaneously and resolve the subcellular details for each cell, like the neutrophil in the central field of view. Recently, we further improved our REFPM illuminator and applied it to higher resolution red blood cell classification without using oil immersion optics. For quantitative phase imaging, we derived the phase transfer function for FPM and revealed the low frequency component of the phase can only be transferred when illumination NA match the objective NA. Based on this finding, we annual LED illuminations matching a 10x 0.4 NA objective length. We present high-speed imaging result of HeLa cell mitosis at 25 Hz with a resolution of 655 nanometer across a wide field of view, 10x field of view, 1.77 millimeter. If we slightly increase the number of annual LED illuminations from 4 to 6, we can retrieve and compensate the waveform aberration, and without resorting to adaptive optics hardware. We demonstrate long-term high-throughput live cell QPI with conventional adaptive optics, computational adaptive optics to secure diffraction-limited imaging performance over an extended period of time up to 51 hours. So far, I have only talked about quantitative phase imaging. It should be mentioned that QPI is not a true 3D imaging modality, so we can only provide a cell profile or topology. In order to realize true 3D imaging and recover the volumetric reflecting index distribution, we need to use optical diffraction tomography. Nevertheless, conventional ODT methods still relies on coherent illumination and complicated sample rotation or beam scanning devices, preventing their widespread use in biomedical community. To solve these problems, we developed a systematic series and methods for non-interferometric optical diffraction tomography. Since these methods are based on intensity-only measurements, we are also call them intensity diffraction tomography, IDT. We propose the transportal intensity diffraction tomography, which can be viewed as the extension of the TRE from 2D QPI to the 3D ODT. In addition, we derive a 3D optical transfer function or the partially coherent illumination, but capture a 3D intensity stack through scanning and followed by a 3D deconvolution based on the phase OTF. We can directly recover the 3D reflecting index distribution of the sample from the 2D intensity stack directly. Similar to the 2D case, we found that matched annular illumination aperture is optimal for ODT in terms of both resolution and signal-to-noise ratio. Based on this annular illumination, we demonstrate the label-free 3D tomography imaging of Jariwala at incoherent diffract limit resolution. TIDT can also be implemented based on sequential LED illumination and 3D synthetic aperture to further obtain a uniform transfer function, enabling label-free 3D imaging of cell dynamics with higher resolution and high contrast. We also extend FPM from 2D to 3D and developed a new 3D computational microscopy approach termed Fourier ptegography diffraction tomography, FPDT. FPDT employs low NA intensity-only measurements and incorporates high-angle dark field illuminations, significantly improves the imaging resolution in both lateral and axial directions. With FPDT, we present the highest throughput ODT results with 390 nanometer lateral resolution and about 900 nanometer axial resolution across a 10x FOV of 1.77 square millimeter. The whole field of view can accommodate about 4,000 HeLa cells or 20,000 red blood cells simultaneously, revealing its potential for high content 3D imaging of large population of cells. Recently, we further improved FPDT by illumination multiplexing and sparse annular illumination, significantly improving the data acquisition efficiency. The full field of view high resolution 3D imaging result of HeLa cell has verified that the multiplex annular illumination scheme can significantly decrease the data boundary requirements without compromising the high throughput 3D imaging quality. The 3D imaging speed can be further increased if only matched annular illumination is used, enabling dynamic 3D label-free imaging of living C. elegans at 10 Hz. Based on this above-mentioned key theory and technologies, we developed several smart computational light microscopes, translating the concept into standalone instruments. For example, by combining a programmable LED ray and a tunable lens, the oscilloscope is able to realize quantitative phase imaging, bright field, dark field, Reinberg illumination, and differential phase contrast with a simple mouse click. To summarize, our research has opened a new era in which strict coherence and interferometry are no longer prerequisite for QPI and ODT, proving the. Finally, we should never forget Abel's remarkable theory for microscopic image formation as summarized in Zenik's Nobel lecture. The microscopic image is the interference effect of a diffraction phenomenon. I also greatly appreciate Gabi's comments. Non-interferometry computational phase retrieval methods eliminate the need for an interferometer, but the interference of light is still the fundamental process for recording the phase phenomenon. Finally, I'd like to thank my students, colleagues, and collaborators. All the work I presented today, I finished after I started SR Lab and NGUT, and we are just on the way now. Thank you for your attention.
All right, thank you, Chao, for your very nice talk. Any questions from the committee? Yes, Edwin.
This is fantastic. Thanks for this presentation. Very exciting and quite a bit of depth and breadth at the same time. So I had a question regarding the first part of your talk where you were talking about transport of intensity-based reconstructions. Two things. Can you tell us more about the reconstruction speed, like the effective frame rate that you have in those kinds of solutions for, let's say a unit millimeter square area? What kind of frame rates do you typically get? And the second thing is, can you tell us more about the resolution that you can maintain? You mentioned something on the order of a few hundred nanometers, a couple of hundred nanometers. What is the smallest phase difference that you can maintain that resolution? And what kind of a noise floor do you have for phase where you lose that resolution? So kind of like the trade-off between phase contrast and resolution that you observe in your reconstructions.
Yeah, thank you, Professor Ozkan, for the very important question. The first question is regarding to the imaging speed. Actually, the imaging speed depends on the acquisition speed and the computation speed. So in our system, actually, because if we use a conventional microscope with a Z stage, actually the speed is limited by the Z stage speed. So if we use a tunable lens, actually we propose a paper based on a tunable lens-based TRE. So this scanning speed can be significantly enhanced. So the acquisition speed is no longer the limit for the final QPR imaging speed. So in this case, so the computation speed is my limitation factor. So in this case, if we implement all the algorithm in C++ instead of MATLAB, so we can do everything in real time. So as I demonstrated by our microscope we have built, so actually we can realize 25 Hertz imaging speed of the quantitative phase imaging. But actually, if we for photographic microscopy, so because the field of view is very large, and we capture quite a lot of intense data. So if we do the synthetic aperture, the data amount is quite large. And the final reconstruct image, actually the intense image we synthesize in the Fourier space. So the final resolution is quite high. So the data amount is quite large. So in that case, we cannot realize very high frame rate in that case. So regarding the second question is the sensitivity for the phase measurement and the trade-off between the resolution and the contrast. So it's a very important question because actually we know the classical interferometry is a very important approach for measure phase, and the sensitivity is quite high for the interferometer, just like a LIGO. Actually, it's a kind of very long, a kind of macro interferometer with a very long distance beams. So in our phase retrieval method, because there is no interferometry, we don't use the interferometer. So in this case, we get better image quality, but at the expense of lower sensitivity for the phase measurement. In our case, for example, so for measuring the microlens array, so the imaging for the phase sensitivity, and we converted it to the height of the microlens. So it's about 15 nanometer for the Z depth resolution if we measure topology of the sample. So if we, and another very important thing is actually the transfer function is frequency dependent for the phase measurement based on TRE. And for the interferometry, actually it's a uniform transfer function. So in this case, this means for TRE phase imaging, so the response for different spatial frequencies are different. So are different. So in this case, the signal-to-noise ratio are different. But in our cases, we use annular emission to enhance the resolution and to our best to get a smooth transfer function to within the differential coherent limit. In that case, so we can guarantee the both resolution and the signal-to-noise ratio. But they're not comparable with the conventional interferometry techniques like the digital holographic microscopy. Thank you for your question.
Thank you.
All right. Any other questions? I'm an outsider of your field, so I have a basic physics question. At some point, you mentioned the low frequency information can only be retrieved when two of the NAs match to each other. Maybe can you give some physics intuition about how to understand that conclusion?
Yes, it is a very good question because actually, for a microscope, actually the final resolution obtained by optical microscope depends both on the NA of the illumination and the objective length. So for normally in a conventional incoherent microscope, we doesn't care about the illumination because actually we just open up the condenser, we can actually get an incoherent image. But for our phase imaging, there is no way to do that because actually there is no phase contrast for incoherent microscope. So we need to do coherence engineering. So in this case, for your problem, for your question is that in Fourier ptychography, so we need to get phase transfer function at broad coverage because the phase for the low frequency phase is quite important for obtaining high precision measurement. So in this case, if the emission NA, it just can fall in the NA that allowed by the objective length. In that case, we can get the strong contrast at low frequencies. But if the emission NA is smaller than that value, so the low frequency phase component can into intensity. That means if we can capture intensity, there is no intensity response phase contrast for low frequency phase components. So if we do the deconvolution, we feel there will be phase low frequency missing problem. So in that, so based on that findings, so we propose so-called annular illumination FPM. In that case, we can transfer all the low frequency components for the phase information. In that case, we can obtain both very high resolution large field view imaging results, but we can also get very nice reconstruction for the cell low frequency components. For example, actually the low frequency component is very important. Otherwise, we can get some artifacts like the halo. Thank you for your question.
Sure. Professor Lan Yang, do you have a question?
Yeah, Professor Zuo, thanks a lot for the wonderful talk about this non-interferometric phase imaging. So these days, deep learning, machine learning has been widely used for imaging. Can you comment on how machine learning can further enhance your image modality?
Yeah, it's very important question. Actually, we have explored this direction because actually deep learning is a very nice tool for actually for us to solve the computation imaging problem, because actually all the computation imaging techniques can be reformulated as an inverse problem. So actually a lot of problems are nonlinear inherently. So solve the nonlinear problem is very challenging. For example, in Fourier telegraphy, we need to do phase retrieval. We need to do iterative phase retrieval. Actually, because for the TRE, we can linearize the phase retrieval, but for Fourier telegraphy, there's a lot of computation involved. And Professor also has done quite a lot of work about the phase retrieval and the lens-free microscopy in these directions. So we are also want to solve some very challenging issues. For example, how to recover actually the 3D reflecting index from 3D intensity measurement actually is non-linear problem, because we actually based on some assumption like the weakly scattering, the first order border observation or rate observation. Actually, there are a lot of samples they are actually strongly scattering. So in that case, we cannot recover very good reconstruction results by using our linear reconstruction algorithm. So we are exploring some new possibilities to incorporate the deep learning approach to, instead of using our standard method like solve the transporting intensity, actually is a linear differential equation. And for iterative phase retrieval, actually is there some very limited, very slow, very computational burden. So it's a very good direction, and we want to explore the possibility in our maybe intensity different tomography in the future. Thank you for your question.
Yeah, thanks for your answer.
All right, great. So due to the sake of time, let's move on to our next speaker, Professor Wei Bao, assistant professor from University of Nebraska Lincoln. Wei, please start your presentation.
Okay, thanks, Shaw. Thanks, Shaw, for the kind introduction. And thanks everyone for organizing these wonderful events. I think talking after Deep may just simply make my job a little bit easier. So today I'm going to talk about our work at UNL using halide perovskite for exciton-polaritons applications. As Deep already mentioned, our work is mostly inspired by the Bose-Einstein condensation in the cold atom. A little bit introduction on here, since maybe the audience are not so familiar with this so fundamental basic things. So as we all know, fundamental particle can be classified as a fermion and a boson. For boson particle, if you try to go to lower and lower the system's temperature simply by cooling the system cooler and cooler, the ground state of this system will become more and more occupied. Across a certain transition temperature, the ground state becomes massively occupied, as demonstrated by the cold atom system. For example, with the rubidium atom, you can see as the temperature go down to 170 nanokelvin, which is 9 order magnitude lower than the room temperature. It's probably one of the lowest place of temperature in the Earth. The Kx equal to Ky, essentially the system's lowest energy, kinetic energy spot, become massively occupied. So the direct consequence of this wonderful phenomenon is you now, instead of dealing with very small object of each individual atom follow quantum mechanics, because all the atom is massively occupied the ground state, you have a macroscopic sizable object which has a build quantum coherence. You have many atoms, but they behave just like one single atom. to be easy manipulation. So smart people quickly realize with such a setup, you can also impose on them with a periodic potential simply by laser interference in the very cold atomic chamber. So in this way, you are distributing evenly this cold atom BEC into this artificial pocket of this potential. Luckily, between atoms, you also have a little bit of interaction among different sites. So now you have a quantum object distributed in the periodic potential, very similar with you have real atom distributed in a crystal structure in the 3D. So essentially, the whole field opened up a lot of the things for quantum simulations for solid state, very hard to understand condensed matter physics systems. However, one of the difficulties, as you may realize in these settings, is you have to go to very low temperature, 170 nanokelvin or even lower, which is not so convenient. However, if you do a little bit systematic check about the critical transition temperature about the boson system, you quickly realize the transition temperature only solely rely on two parameters beside a bunch of the constants. That is one of the effective mass of the boson particle, and then the effective density you can achieve with the boson system. So a little bit simple mathematics, you will show if you have a boson system with a lot higher density and a lot smaller effective mass than the cold atom, the transition temperature is not necessary to be the lowest on the Earth. In fact, it can also go to room temperature. So for this audience, I think everyone think about photon, right? Because photon can go to very high density and the effective mass almost zero. But unluckily, photon has no interaction fundamentally in between them. They are really bad for quantum simulation or emulation in that sense, if you realize a photon BEC in them. So to overcome this, smart people quickly propose we can actually create a photon with effective interaction by forming a new hybridized quasi-particle called Exciton-polaritons via strong coupling. So how that works? So essentially, we start with excitonic semiconductors. And if this excitonic semiconductors with a bright quantum yield, strong absorption, you put this strong excitonic material into a good optical cavity, because this exciton will recombine. And if the majority of this path is towards the emitting photon, the photon will trap by the cavity. And the photon will be strongly absorbed by the excitonic material again. So exciton become photon, photon become exciton, back and forth. So we entering the strong coupling regime. Any photon you detect outside the cavity, they already experience the energy level of exciton or energy dispersion of photon. So you cannot tell this is exciton level or photon level. So they become a new quasi-particle called Exciton-polaritons. So one can view that as a quantum superposition of photon states and exciton states of the originally exciton energy diagram of photon or the cavity photon diagram. In the EK diagram, they become now hybridized, form a Rabi splitting and the new two states called the upper polariton and the lower polariton. Luckily, you realize the cavity photons dispersion curvature is pretty much similar as the lower polariton's curvature. So instead, the polariton has an ultra small effective mass compared with cold atom, pretty much similar with cavity photon. And what's more exciting about this, the exciton part provides the interactions you need for quantum simulation or emulation, and also the nonlinearity. You can simply pump the system with a higher laser power and increase the boson particles density. So the N can be high and the effective mass can be really small in this system. So indeed, people are very excited about the system, and they start with MBE grown catatelluride quantum well and put this into the DBR dielectric cavity. And they maintain a constant temperature by simply increasing the system's particle density. You quickly realize similar behavior of about boson-Einstein condensate. And then the system also massively occupy the ground states. As you increase the pump power, they gradually occupy the energy minimum states of the lower polariton states. You will also observe a little bit of blue shift, but that is essentially the exciton-exciton interaction generated, which is ideal for some of the quantum applications. So, however, despite these exciting things, there's you may heard a little bit from Deep's talk. There's a lot of the effort to try to make a quantum simulation emulation platform and room temperature for the polartonic system, but it's remain elusive due to many of these materials imperfections. So our great inspiration of the work coming from our friends in the solar cell community who discovered the excitonic halide perovskite. This material has a strong absorption. and also strong photoluminescence, which is very good for polariton applications. What's more exciting is this material and also has a very stable, robust exciton at room temperature against the thermal fluctuation of 25.8 MeV. And what's more is, despite you see a lot of the perovskite, cesium lead bromide, or even inorganic one, no matter you have organic component or non-organic component, they are all shows Weinert mode exciton type. So essentially, the exciton are interactive among each other. They are not a localized Frankel exciton of this organic material, which makes it almost the ideal things to do. So to make the final ultimate goal towards to do some quantum simulation or emulation with the system, we really want a homogeneous platform. We want our artificial atom behave similar among different sites when you distributed them into a periodic potential. So to overcome, to really tailor the material property in that way, so we invent some of the growth method. We call this growth under confinement, specially tailored for the highlighted perovskite material. So essentially, the basic scheme is we start with microfabrication, microcavities, and then we deposit the microcavity one-side mirror with gold pillar, control uniformly this gold pillar distribution, and then we flip the two wafer and use wafer bonding to bond them together. Afterwards, we dice them into small chips. Because microfabrication can control this gold pillar thickness with a great uniformities, we now with a chip can show the cavity thickness only variation for about 1 or 2 nanometer among a small scale, which is pretty ideal. And then we apply solution into the cavity, let the crystal directly grow into this. And afterwards, we got very big crystal. As you can see, the method is also general towards multiple material with excitonic component inside it. And then the optical imaging shows homogeneous properties along the thickness. And also, if you do a little bit systematic study by mapping the lower polaritons energy level spatial distribution over a large area, in this specific case, we do 64 by 48 micron area scan, you will see the energy minimum is only has a very small variation, plus minus 3 MeV. This is comparable with the best MB grown material or even superior, for example, gallium arsenide or catatelluride. With this great platform, we want to benchmark one of the landmark experiments in the field. That is the Landau theory of superfluidity. Superfluidity is first discovered by the liquid helium system. One of the dramatic nature, fantastic nature about superfluidity is if you flow the superfluidity against a sizable object, if you are in the quantum superfluidity state, the quantum coherence make the superfluidity can bypass the object without any friction, and also backscattering. So this frictionless flow and the scatterless flow is one of the fantastic feature of liquid helium. And then later on, Landau further investigated the system, and he said, if you flow the superfluidity system at a lower speed, indeed, you don't see any elementary excitation, so you don't see any dissipation, so you don't have any scattering. But if you flow the superfluidity above a certain transition of velocity, you will start to hitting some of these elementary excitation spectrum in the superfluidity system. And then the superfluidity no longer maintain the superfluidity and break. There's a transition predicted by Landau. So in the cold atom, such a experiment is relatively hard to do, especially you try to flow the cold atom in a pocket to against an object. But in the optical polariton case, our experimental setup can be quite easy. We just control the polariton liquid flow speed by resonantly inject the polariton into certain energy we want them to flow and a certain momentum, in-plane momentum we want them to flow. So in this way, we can control the flow velocity of polariton simply by inject a femtosecond laser resonantly into the polariton cavity and then let it evolve freely in the cavity to see the superfluidity behavior. So indeed, we did the experiments, as you can see, when we flow the superfluidity, when we flow the polariton liquid at a very low speed, as you can see at the very beginning, we have pump power very low. You can see a lot of backscattering. When we start to cranking up the laser power, we enter in the BEC state, boson-Einstein condensate state, this Bose-Einstein condensate state rendered system has superfluidity property. And after this transition about a certain pump laser threshold, we will see the backscattering become fully diminishing. And then the K-space also support the discovery. The backscattering at the very beginning we observe, and then later on they fully suppress, which is quite exciting. And then another experiment we did is we continue increase the pump angle. So in that way, we have higher in-plane momentum. And as you can see, as the lower pump power, they show a linearized wavefront because we have very high pump speed across the speed of sound of the polariton liquid. And they also show a little bit the back reflector, back scattering. And afterwards, after transition, the back scattering is not fully suppressed. But what's more interesting is you see the linearized wavefront angle become increased. So such a phenomenon suggests we have a Cherenkov supersonic fluid. Just like you have a normal fluid like air, we fly the jet beyond a certain speed of sound in the air. We see the linearized tone. So which means the superfluidity state has been broken simply by flowing higher speed. So which make our system pretty ideal. This is the first demonstration that a quantum liquid can satisfy the Landau criteria at room temperature. Very exciting. Another thing we are quite interesting to do is to do analog simulation with the system in the spin Hamiltonian. There's multiple motivation about that. One thing is we always have the interest in spin physics. The other thing is like a lot of the real world problem, like travel salesman's problem, which is very hard for optimization, but they all can be formulated as a spin model. So for the spin model, you can up and down as Ising model or in-plane rotation of the spin as XY model. Those are interesting analog machine. A lot of people try to invent. So with the cold atom, they also has early endeavor try to do XY spin Hamiltonian. However, as I don't want to go to more detail about it, but for cold atom system, because it's very hard to visualize, you have to measure the momentum space in the experiment and then later on compare with theory. There's no direct visualization in between the different spin states, how they interact with them. But anyway, greatly inspired by this early success with cold atom, we come with a spatial light modulator way to optically imprint the polariton lattice directly into our perovskite system. So what's good about it, we can visualize this spin interaction. For example, we have two condensates optically imprint by spatial light modulator here. And then you can see the interference create a dark spot, essentially suggests one spin up and spin down. They are deconstructively interference with each other. So one can tune this spin coupling term Jij in between different sides simply by changing the pump configuration, which is quite interesting. Besides, because our system is very large, pretty ideal for doing some of this quantum emulation stuff, we can also imprint a large spin lattice simply by here we show 4x4 or even 10x10 or even triangular lattice, which is one of the interesting configuration for demonstrating spin frustration states. So without going into further detail, I want to summarize our work. So I hope in this short period of time, I convince you exciton-polaritons are light matter quasi-particles. It's combined with exciton and photon that can show Bose-Einstein condensate on some of these quantum behaviors very similar to cold atom, but at a much alleviated temperature. So our work demonstrates a critical step towards a platform that can do quantum simulation or emulation at room temperature. This is enabled by both the excellent highlighted perovskite materials property and also our approach to make a polartonic device. So with that, I want to acknowledge my group members, collaborators, and especially thank to Professor Natalie Berloff, who generate a lot of inspiring discussion and encouraging us along the work. Lastly, I want to thank the funding agency of ONR, NSF, and the Nebraska Mercy. With that, I want to take any questions from the audience. Thanks.
All right, great presentation. Any questions from the committee members? Yes, Professor Pullman.
Yeah, a very interesting talk. Thanks very much. It's very impressive how you can assemble these layers and how good the quality of these excitons is and their coupling. You mentioned the spatial light modulator at some point to tune basically the assembly and self-assembly. Can you say a little bit more about that, how that works?
Right. So, yeah, thanks. Albert for the nice questions. So I think this is very nice. So instead, the spatial light modulator is the enabler. You can tune this pretty much arbitrary dot shape. It gives us a lot of freedom. And also, I want to emphasize, I didn't have time to talk, but the spatial light modulator enable another new functionality compared with cold atom. In the cold atom, the interactions is rely on nearest neighbor interactions. But with a spatial light modulator, one can directly modulate it, the Bose-Einstein state, condensate state, the phase of it. So one can use the spatial light modulator even to construct non-nearest neighbor interactions, which is relatively new, not capable with cold atom. But we are just using traditional spatial light modulator to create those wave patterns very easily, just imprinting them on the platform.
Fantastic, very insightful. Thanks very much.
Thanks, Albert.
So yeah, maybe Professor Neship have a question.
Yeah, I have a curiosity question. What are the quality factors? Sorry, apologies. What is the quality factors of the cavity that you're using?
Yeah, so thanks to Dragomir for the nice questions. So the quality factor we use is about 2000. It's not something very high because we don't need something very high at this moment. But indeed, some people in the field demonstrate 1 million or 10,000, very easily with, or I shouldn't say very easily with MBE grown substrate, because they can grow this with multiple days and then to fully release the stress in there. So in this way, the ferroperl cavity can be very high. But in that scenario, you will suffer a little bit low temperature operation. For us, we do room temperature. At this stage, we can achieve something several thousands very easily. We didn't push very hard with more than 10,000 simply because our mirror is deposited by ion beam sputtering, and those mirror will have a little bit stress, a little bit bending in the long range. So you easily got a Q factor about 10,000, but beyond that, it's relatively hard. You need to manage the stress of the mirror. I hope that answers your questions.
Yeah, thank you. I actually have two follow-up questions. So one is, you mentioned that you actually inject femtosecond pulses through the reflector. So does this fit through this high quality mirror?
Right. So as you can see, the polariton, once you form the polariton states, you measure the white light reflectivity, you will see 2 deep, which shows 1% or around that deep. So that deep is because the excitonic material, before they go to the condensation states, they will be a little bit absorptive. So you will see measurable deep in there. So essentially, before condensation, the cavity Q factor will be lower than the cold cavity, simply because you have absorptive material. But once they go to condensate at the bottom, you will see the true warm cavities Q factor. Essentially, this is like, especially at the threshold, the gain and the loss are balanced. So that's the true cavity we make. But we are optically inject resonantly above this condensation location. So on that location, the line width, we have finite line width, and also the deep to inject the femtosecond laser with a efficiency like 1 or 2%. It's not great, but we can inject resonantly there.
Understood. So if I may, just one final question. So what do you see the prospects of using sort of in-plane cavities or in-plane modes for such condensation?
May I ask you to elaborate a little bit? What do you mean the in-plane mode?
So what I mean is if you use like a BIC type states in photonic crystal type kind of slabs of the material.
Right. So yeah, this is a great question. Indeed, there are some of the pioneering people trying the BIC crystal, such as Professor Daniele Savinto in Italy. So they published a Nature paper on that recently this year with the gallium arsenide crystal. But with that, I want to say that it's good and bad. With the BIC crystal, you are creating a potential landscape, and they show wonderful, optical properties, which is good. But the bad thing is you don't easily reconfigure it. So we, like spatial light modulator, a lot easier because the tunability, the flexibility, the manipulation you can do is simply on the level of cold atom, level. So we don't like pattern too much. the things. But certainly one can pattern to study it onto a specific question or bring new potential landscape into the field of study.
Thank you so much.
Thanks.
So I have one question. When you create this large lattice for studying the spin models, spin Hamiltonians, I mean, one of the criteria if you can do quantum simulation is that the coherence of each qubit is much larger than the interaction strengths. How do you compare your coherence of each side with their interaction strengths?
Right. Yeah, sure. Thanks for the nice question. Indeed, ideally, you want to fully equilibrium system. But for us, we have a Hermitian system. We have loss, right? And essentially, the photon has a finite lifetime. So, but as long as the polariton lifetime is enough to sustain the nearest side interactions or beyond the side interactions, everything will be fine. For us, we currently has the polariton which can travel in this cavity very long, 20, 30 micron. Our nearest side is about 5 micron. So they are generally fine. The lifetime is longer than the interactions time we need. But you're right, if we try to do something with a distance of 100 micron, it could be a problem because the polariton just die out without any interactions.
I see. So from that perspective, does that set a ultimate limit on the scale of your spin systems? Or you are currently limited by some other factors, the scale of the system?
The scale of the system is not limited purely by that, because we don't need to construct a spin system which put them 100 micron apart. We want to put them close enough, they are independent condensate, and then we tune the interactions among them, the interaction we want them to be. So typically nowadays it's about 5, 10 micron, that's sufficient. So currently we don't see the spin system limited by any of that, but it could be one system, as I answer Professor Alberto's question, is like we try to build non-nearest neighbor interaction by spatial light modulator. In that case, the lifetime could be a limiting factor because we want to read out the time, the states and the feedback, right? The feedback time has to be faster than the polariton lifetime.
Got it. Yeah, makes sense. Are there any last minute questions? All right, if not, thank you again, Wei, for your very nice presentation. And thanks. Let's move on to the next speaker. Our next speaker is Professor Yating Wan from Abdullah, King Abdullah University of Science and Technology. Yating, please take your time.
Thank you. Can you see the screen now?
Yes.
Okay. Thank you for the introduction and for the opportunity to present my work in this great forum, Writing Star of the Light. This is Yating from KAUST. In this talk, due to time constraints, I'll focus only on one of my works to make it clear, integrated silicon photonics with on-chip lasers. So what is integrated photonics? Integrated photonics can minimize optical functionalities into a compact form factor and allows for the improvement in performance as well as the reduction in terms of size, weight, power consumption, and cost. Previously, the photon integrated circuit has been entirely based on indium phosphide-based and these 3-5 materials, but now we're switching to silicon. We are making photon integrated circuits the same way electronic integrated circuits are made that can leverage from the most advanced CMOS processing with low price, high yield, and good thermomechanical properties. A variety of photonic devices can now be put on silicon, including low-loss waveguides, modulators, detectors, but it's hard to integrate all the photonic elements on silicon, especially the lasers. So silicon is indirect bandgap material that makes it unsuitable for high-performance lasers, with the only demonstrated laser in this material system having orders of magnitude higher spectral current density than what is achieved in direct bandgap 3-5 materials. Therefore, the 3-5 laser is typically off-chip, where optical packaging with optical alignment occupies over 90% of the total cost. Heterogeneous integration is a revolutionary story, and it bonds the unpatterned 3-5 thin films to silicon wafers at the early to middle stage with a coarse alignment, and then define the device by lithography on a full wafer scale. With the chip maker Intel, this device was used in mass production lines after just 10 years of its demonstration, and is now generating over $1 billion of revenue nowadays. However, the use of 3-5 substrate for the laser growth can still be costly, and that imposes a limit on the maximum bonding size set by the largest available 3-5 substrate, which is typically no larger than 200 mm for GaN arsenide and 150 mm for indium phosphide, much smaller and more expensive than the silicon counterpart. So considering the 3-5 substrate cost, monolithic integration through direct epitaxial growth is a more economically favorable option and also provides the best natural heat sinking for laser operation. However, the fundamental material difference between the 3-5 and silicon during the epitaxial growth can generate a high density of crystalline defects. These defects act as non-radiative recombinant centers that grow with the device operation into this location network, and finally, there's a large network of dark line defects. This degrades the device performance and shorten lifetime. So while research has been conducted since the 1980s to grow quantum well-based lasers directly on silicon, aging tests show the maximum device lifetime less than 200 hours. So in this scenario, how can we improve 3-5 laser on silicon by orders of magnitude? So the strategy here is that we deal with the active region, and quantum dots can be used instead of quantum wells. So what is quantum dot? Quantum dot represents zero-dimensional particle in a box-like quantum confined structure that can be formed through the self-aligned self-assembled process using indium arsenide and GaN arsenide layers. So due to this three-dimensional confinement carriers, a complete localization of electrons and holes can ideally give rise to a sequence of dollar function-like density of states possessing analyte degeneracy. So as a result, quantum dots have promised a lot of performance advantages over its quantum well counterparts, including high temperature tolerance that allows for robust CW operation up to 220 degrees C, low special current that is capable to support low energy consumption. More importantly, for line width enhancement factor, or we call alpha factor, so you see the typical value for quantum wells is 3 to 5. But quantum dot is 15 times smaller. So from this scaling factor, the critical feedback level is closely related to this alpha factor. And quantum dot had over 50 dB increase in this value compared to quantum wells, such that even with 90% of the light reflected back to the laser, the optical and optic spectrum show no coherence collapse. On the contrary, for quantum well devices, complete coherence collapse will happen just at a low feedback level of -25 dB. So this is very important to data communication system because with this reflection-tolerant quantum dot active region, we don't have to add isolators into the system to block the undesired reflections, which is bulky, expensive, and can greatly complicate the packaging and add additional insertion loss. In addition, for carrier diffusion length, the typical value for quantum wells is around 10 micron, but quantum dot is 10 times smaller. In the case of a relatively high spreading desiccation density, carriers in the quantum wells are free to move around in the plane of the well and can encounter a defect before recombine radiatively. In a quantum dot, however, the chance of carrier mitigation to dislocations and be trapped by the dislocation trap states was greatly reduced. For example, in this TM image, the red points refer to the defects, and the yellow dot refers to the quantum dots. You can see that even with this very high spreading dislocation density, because the dot density is still more than 2 orders of magnitude larger, and because each dot is independent, one defect in the active region can only kill one or a few dots, and the majority of the dots are not affected, so device can still work efficiently. So this much improved defect tolerance gives rise to record long device lifetime on silicon. So while you remember that the maximum lifetime of quantum well laser grown on silicon has only 200 hours after several decades of research, our generation 1 quantum dot device already show a lifetime of 800 hours at 30 degrees C. And after these generations, our most recent results show 1 million hour extrapolated lifetime at 80 degrees C. This is a remarkable improvement compared to our first generation of device, and also orders of magnitude longer compared to any previous lifetime test of quantum well lasers epitaxially grown on a silicon substrate. So there's a lot of recent progress of quantum dot devices grown on silicon, such as the sub-wavelength optically pumped microdisc lasers, this sub-million special electrically injected microwave lasers, this couple cavity tunable lasers, this high-speed DFB lasers, this isolated phase system demonstration showing a path towards high-volume, low-cost transceivers that can be scaled to beyond 1 terabit per second. This 20 gigahertz Moloch lasers with high channel count and excellent RF performance, high gain, high saturation output power amplifiers, and ultra low dark current voltage detectors. But in addition to the improvement of material quality and individual quantum dot device performance, we are particularly interested to achieve low loss active passive coupling with the 3-5 quantum dots with the silicon waveguides to form a fully integrated photonic circuits. So the most challenging part here is that we need to change from indium phosphide-based quantum belt epi to gallium arsenide-based quantum dot epi, and thus we need different material systems and completely different device design and process optimization. So here the schematic showing the quantum dot laser integrated on the SOI substrate consisting of this hybrid 3-5 silicon active region coupled to a passive silicon waveguide. So the process starts with the passive waveguide process, subsequent wafer bonding and the substrate removal, and then we add the 3-5 mix-up precisely down to the end contact layer and keep the etching uniformly across the whole wafer. So a lot of process optimization was devoted to achieve the smooth, straight, and accurate etching sidewall, so that we can get this very nice 3-5 taper to shape the hybrid mode to the silicon waveguide mode. And after the P-mesa paddling, so the N-gas contact layer was tapered in a separate short transition, and here metal stacks are deposited as contact metals. Device was passivated via and was opened for probe metal, and here is the final device. So the laser shows a threshold current of 4 million, Simon observation ratio of 60 dB, CW temperature of 75 degrees C. But what I want to emphasize here is the modulation bandwidth and the line width. So a high modulation bandwidth has always been very difficult to attain for quantum dot lasers. Today, even the best reported value on native substrate is around 10 gigahertz. But here we got a record high value of 13 gigahertz achieved just with polished facet. And there still remains a lot of room to further improve it, adding a pervia facet coatings, deposit metals on a thicker dielectric for low capacitance, etc. And for laser line width, which is closely related to alpha factor, which is due to the 15 times smaller alpha factor in quantum dots compared to quantum wells. We got 26 kilohertz here, which is an order of magnitude lower compared to the typical solitary quantum well laser line width, which is several megahertz. So this table compared the device performance of this work and the previous reported work, which clearly shows that the laser with the silicon waveguide can significantly outperform the laser without a silicon waveguide in terms of line width, bandwidth, Simon spatial ratio, etc., which we are very excited about, as it shows a synergistic relationship between the unique capabilities of 3-5 quantum dots and silicon, allowing for not only a reduce of cost due to the economic scale, but also much better device performance, exceeding what can be achieved with purely 3-5 quantum dot devices. So when you put the lasers on silicon, you not only get a better substrate, you also get a better lasers. So following this direction, we now cooperate with Intel and is using Intel's 300mm silicon photonics platform to pattern the passive waveguide to be bonded with our quantum dot epi. So Intel Lab recently opened a research center of integrated photonics for data center interconnects. And this work is your first collaborative project with universities and is happening for practical solutions. So by changing out the bonded quantum well attachment material for quantum dot on silicon structures, there will be substantial opportunities to build upon what has been achieved through Intel silicon photonics to both improve performance and reduce cost. So currently, the biggest driver in future developing silicon photonics is for datacom. But beyond data centers, this dense device integration with on-chip lasers will be critical for a number of envisioned future applications, neural networks, co-packaged ASIC, and quantum communication, etc. So with on-chip laser sources, all the optical signals will be confined within an integrated circuit package for the efficiency, stability, and scalability. And by leveraging the attractive features of integrated silicon photonics and its advanced Intel PDK and the process on-chip lasers will revolutionize these applications for substantial performance gains, green solutions, and mass productions. So to conclude, we have achieved a lot of progress in the last 6 years in on-chip lasers with silicon photonics. And what we want to emphasize is that laser integration for silicon photonics is definitely the key to advanced photonic integrated circuits. And we look forward to transform this technology to something that can really influence the industry. And finally, and most importantly, I would like to thank my supervisor, Professor John Bowers, and the UCSB group. And I also would like to thank my collaborators in Intel, HKUST, Harvard, HP, Quintessent, Cardiff, India National Lab, IQE General University, CUHK, National Central University, and Shanghai Tech for contributing so much to this work. With that, I'm ready to take questions.
All right, great talk. Are there any questions from the committee members? Oh, a lot of questions. Maybe we go first with Yidong.
A great presentation. I have a very quick question. You mentioned lifetimes on the order of several tens of years. Can you tell us a little bit more about how do you quantify those, how accurate those quantification methods are? That would be kind of my quick question.
Oh, so this all the lifetime test was done by Intel. So you can be sure that this was done by like industry standard. So basically, they age the lasers at different temperatures and constantly like measure their special current, and then they can project like when like you can estimate like when the time the special current was decreased to half of its value, like increased to half to that double its original value, and then you can, based on that, you can get an extrapolated lifetime of like 1 million hours. So all this lifetime test was done in Intel using the most stringent industry standard.
So it's an experiment that is extrapolating in time, but how do they model all the complexities of the system? So in other words, can't there be random processes that are not taken into account that could happen later in the use cycle? In other words, I'm trying to understand the accuracy of such a large extrapolation to 100 years at 35 Celsius. How is that possible? Perhaps I'm missing something. It requires very sophisticated modeling to avoid any stochastic events that break your extrapolation. Did I miss something, or maybe?
Yeah, so there are several things to be considered. First, we have several metrics, including the special current, and we also model. We also check the power and the differential gain. So there are something. There are like 3 elements of matrix we're looking at. And the second, you have to age for like certain times. For example, like 1 million extrapolate lifetime was based on like 5,000 hours of lifetime test. So you have to be long enough. The lifetime has to be, you have to measure long enough to get a convincible result.
Okay, thank you.
All right, Albert.
Yeah, to add on the previous question, by the way, also in photovoltaics, this is a big question. How do you extrapolate lifetime over a long time? I think these models are actually very well developed and advanced, and but of course they're important here too. My question is about the polarization dependence here. It was a beautiful talk. I had never thought you could make such nice waveguide lasers on a silicon substrate, and so at so low thresholds also. But the way you grow the quantum dots make me think there could be some polarization dependence, and for lasers and amplifiers, it's important to know that.
For that part, I think it's a very interesting topic to like we need more investigating into this area. But for now, we haven't done much work about it.
I see. And if I can ask about the lasing threshold, Do you understand what the particular value of the current is for the threshold? Do you have a model that involves maybe the carrier recombination and other processes so that you understand that threshold?
So this is just like experimental results. So like we try, so the threshold definitely related to a lot of things, including the epi design, the process, and yeah. So I think the main issue here is that we do a p modulation doping or like UID doping. So that is like for the epi design, that's a main concern here. And for the device part, definitely the loss is a great issue. And I think when we are trying to like leverage the Intel process, so we get like ultra low silicon waveguide, and that can actually form very low loss laser cavities, and that can further reduce the loss and reduce the laser threshold. Yeah.
Okay, that's clear. Thanks very much.
Next question. Yeah, Professor Lan Yang.
Hi, Dr. Wan, thanks for giving a wonderful talk. So we know the chip scale laser is very important for integrated photonics. Can you comment on pro and con of this photonic crystal quantum dot based laser versus 3-5 based laser for chip scale lasers?
So quantum dot laser is actually the quantum dot is like we are using indium arsenide quantum dots. So it's like 3-5 lasers. So I think probably you are asking like the monolith integration approach and the heterogeneous integration approach, right? Yes, I think monolith integration is more economically favorable and it's a very promising approach towards a high density and a large scale silicon photonics integration. And actually, in our most recent results, we also like are able to grow this quantum dot laser on 300mm pattern silicon wafer with a buck couple configuration, and also some other group also demonstrate the efficient power coupling from the buck couple silicon waveguide. But I have to say that there's it's still in the preliminary stage. There still remain a lot of challenges to solve, and currently the vast majority of the research into the epitaxial integration still focus on lasers, and more work needs to be done to integrate the lasers with the rest components to form a fully photonic circuits. Heterogeneous integration, on the other hand, is quite mature. Much more mature than the monolith integration. However, the associated technical complexity is still considerable, in particular with respect to the stringent requirements of the ultra clean and extremely smooth surface before the bonding. And moreover, as I mentioned in the previous talk, the use of graphite substrate for laser growth can be still costly, and that can impose a limit on the bonding size. So I think looking forward, whichever approach that can best leverage the economics of scale of silicon while maintaining the highest yield will win. So we will see.
Okay, thanks a lot.
Great. Any other questions? Yes, Professor Ming Chu.
I have a question about the operation wavelengths of your quantum dots. So how widely you can tune this working wavelengths range?
Yeah, I think that's a very good question, and I think that's one major advantage of quantum dots over the quantum wells. So the quantum dot, like for now, it's like central wavelength is 1300 nanometer, but actually the dot can be tuned quite wide. Actually, we can experimentally tune the full width high maximum of the PL to 131 nanometer. So that's pretty wide, and this is be done by because the quantum dot there are 5 layers of quantum dots, and each layer you can center it to different wavelengths. For example, the center one is 1300, and the other layer can be tuned to 1250. So it can be pretty wide and flat PL, like up to 130 nanometer. So in that case, it's also very good comb source.
Maybe I will ask the last question. So with so many nice prospects of these integrated lasers on silicon, what is your vision on your next step in your own group?
I think one thing I think it's from device to application levels. As I mentioned, there are so many applications that with on-chip lasers, like we can do, like for example, like quantum communications, right? Like neuromorphic photonics, like with on-chip lasers, like the efficiency will be definitely totally different. And I think another main thing that we have to be very careful to see is that we still have to be very careful to see if optics will really enable the on-chip communication and enable optical network on chip, because there are three key metrics for future interconnect technology: bandwidth, density, and energy efficiency, and latency. And this will only happen when optical interconnects can clearly outperform electrical interconnects on the combination of these three key metrics. And the projection this typically means like 100 femtojoule per bit system energy target, and with about 10 to 20 femtojoule per bit allocated for the optical source. So in this regard, we have to further optimize the laser, and we need to move from these aggregated architectures to be integrated on the photonic circuits. Yeah, and also like we have to evolve the whole photonic circuits from the pluggable transceivers at the periphery of the board to co-packaged optics and electronics, and to 3D integrate photonic circuits and electrics integrated circuits. And also we have to increase the number of devices on a single signal photonic circuits, so to keep increasing this number. And I think the key is we have to further improve the performance of on-chip lasers, and also increase the number of devices.
Great. Thanks for the clarification. All right, great. Thank you again for the very nice work and very nice presentation. We will move on to our final speaker of today, Professor Qiushi Guo from Caltech. He's a postdoc from Caltech, but incoming assistant professor at cooling.
Okay, can you see my full screen?
Yeah, very well, and we can hear you well.
Okay, thank you, Shuo, for the kind introduction. I'd like to thank the organizer and the committee for giving me this opportunity to share my research with the public. So, one second. So my research focuses on chip-scale photonic devices. So here I want to introduce the grand scheme of my research by talking about two basic properties of light, wavelengths and timescale. So in the visible and near-infrared spectral region, we already have many commercialized chip-scale technologies that we are using every day. And it's important to note that some of them can operate at relatively high speed with a time scale down to nanosecond or picosecond. But however, on both of the axes, you can see we still have a lot of open rooms, which means that the chip-scale photonic devices are very underdeveloped, but they contain a lot of opportunities. For example, in the medium-infrared spectral region, we have numerous exciting applications such as phase-space communication, breath analysis, and thermal imaging. And also on the timescale axis, femtosecond lasers and systems are proven to be extremely useful for futuristic ultra-fast classical and quantum information processing. But currently, the development of chip-scale photonic devices are facing two grand challenges. The first is how to efficiently detect and generate near-infrared light. And second is how to efficiently generate and process ultrashort light pulses. I also envision that in the future, at some point, these two directions can merge together. This will lead to some really brand new technologies. For example, the chip-scale medium-infrared femtosecond laser system, which will play a crucial role in future communication and healthcare. So my first PhD research is trying to address the first challenge, that is how to efficiently detect medium-infrared light at room temperature. So detecting medium-infrared light at room temperature is challenging because the photon energy of medium-infrared light is very low, which is even comparable to the thermal energy of thermal radiation in the environment. So we really need some new device and new mechanisms to tackle this challenge. So during my PhD, first of all, I discovered there's a new 2D material called the black phosphorus, which is an excellent material for medium-infrared photonics. So it has a moderate band gap of 0.3 eV. And also by using this material, I have demonstrated the first black phosphor medium-infrared detector in the world, which offers a very high responsivity, high photoconductive gain, and also the very low detection limit of 5 picowatt. So in addition, we discovered something very interesting in black phosphorus. So we found that by simply applying a vertical electric field across the black phosphorus, we can dynamically tune the band gap of black phosphor to even to 7 micron. So this can extend the spectral response of black phosphor to even longer wavelengths of 7 micron. So later, I enter a new, even more challenging regime, which is around 10 micron. So I've discovered a new method of converting or detecting long wavelength mid-wave photons. So I convert long wavelength mid-wave photons into the plasma mode in graphene, and then read out the plasma electrically by using the electrical transport properties of graphene nanoribbons. So conventionally, it's known that in conventional metals, the plasma can decay very quickly, and it's very difficult to harvest them. But in this work, we challenge this traditional understanding by leveraging the very unique hot fiber physics in graphene. So during my postdoc research at Caltech, I strive to tackle the second challenge, which is how to process the information carried by ultrashort light pulses. So the semiconductor carrier dynamics turned out to be too slow for doing this job. So one natural thinking is that can we just use light to process information carried by light, because the light can travel very fast. But however, this is extremely challenging to realize, because in most cases, light do not interact with each other. But it turns out that the interaction between light can be mediated by materials, and this is a subject of study called the nonlinear optics. So when the incident light field is strong enough, the induced polarization of the material has some higher order terms, which can respond nonlinearly with the light. So what we are interested here is the Chi2 nonlinearity, or the second order nonlinearity, which is order of magnitude stronger than third order nonlinearity. So the nonlinear optics has been studied for more than 60 years since the very seminal paper, but till now, the study of nonlinear optics still rely on very bulky tabletop system, which occupies a very large space. So as an electrical engineer, of course, one natural thought in my mind is that can we make a nonlinear optical system fully integrated on a chip? But the deeper level deeper level question to address here is that in addition to just make things smaller, can we realize some new functionalities by integrating things on chip? So very recently, the wafer scale lithium niobate has been commercialized, and this will make it possible to use a nanofabrication process to fabricate large-scale photonic devices on chip. So at Caltech, I developed an entire procedure of fabricating high-quality integrated photonic devices on this new platform. So by optimizing the etching process, we are able to create a very low loss waveguide with a propagation loss as low as 0.2 dB per centimeter. So by making optical waveguide on this platform, we can dramatically increase the spatial confinement of light. So this in turn makes a nonlinear interaction between light and the material much stronger. But what is even more impressive about this material is that lithium niobate is also a ferroelectric material. As you can see from this image, inside the waveguide, the ferroelectric domains can be engineered periodically. So that being said, we can periodically flip the sign of nonlinear coefficient along the waveguide. So we can make a special waveguide called the periodic pole lithium niobate waveguide. So as you can see here, with this special waveguide, the Chi2 nonlinear interaction can happen continuously and strongly without any back conversion. And this is a technique called quasi-phase matching. In addition to the second harmonic generation, with this quasi-phase matched lithium niobate waveguide, we can also do something called degenerate OPA, which is very similar to the reverse process of second harmonic generation. So in this case, we can use the light of frequency 2 omega to amplify or de-amplify the light of frequency omega, just depending on the relative phase between this pump and signal. So this nonlinear process are very well known already. So what can be the new thing we can do with the thin film lithium niobate platform, in addition to just making smaller? So the answer is we can realize something called a spatial temporal confinement. So in conventional bulk lithium niobate, the light is very weakly confined to the waveguide. So in this case, propagation of the ultrashort light pulses will be strongly affected by material dispersion, such as group velocity dispersion and group velocity mismatch. And this dispersion mechanisms can limit the parametric gain and gain bandwidth significantly. But in thin film lithium niobate waveguide, as you can see here, the light is so confined to the waveguide. So the material dispersion can be well compensated by the modal dispersion of the waveguide. So by carefully designing the geometry of the waveguide, we can even engineer the GVD and GMF to be close to 0. So in the temporal domain, you can see the pump and signal can always be overlapped. So this can make the parametric interaction super strong. And also because the GVD can be close to 0, so there's no cross broadening. So using this platform, we can even enter a new regime of nonlinear optics, which offers a very large gain and large gain bandwidth. So to verify this, we perform a parametric gain measurement by using this setup. And here's some measurement results. You can see at some point, we see the amplification of signal at 2 micron. But when the phase is shifted by 180 degrees, we see the de-amplification. So if we operate the device right at the point of the amplification, from this plot, we can see that the gain can be even more than 50 dB per centimeter if the pump energy is slightly beyond 1 picojoule. We also found that the parametric gain can be large enough to even amplify the vacuum noise into a detectable signal. So we found that without injecting any signal at 2 micron, at the output of waveguide, we see a lot of parametric fluorescence at 2 micron. And they cover a pretty wide spectrum range of 600 nanometers. So from the energy of the parametric fluorescence, we can actually extrapolate the parametric gain. We found it can be as large as 100 dB per centimeter at a pump energy of 5 picojoule. So it turns out that our dispersion engineered OPA has the largest gain bandwidth product compared to all existing optical amplifiers. And such a performance is the direct result of the dispersion engineering and the spatial temporal confinement we just talked about. So the parametric amplifier just talked about not only can amplify classical signal, but also can amplify quantum states. So when the quantum state is a squeezed vacuum state, but we know that the quantum states are extremely fragile and they are sensitive to optical losses during the propagation and detection. So here we tackle this challenge by constructing a small-scale nonlinear optical system. So the first part of the system is that OPA, which is utilized to generate squeezed vacuum state. But the second part of OPA of the system is the OPA with a higher gain. So it is utilized to pre-amplify the squeezed light into a microscopic power level. So by utilizing this squeezing and the pre-amplification scheme, we can make the quantum states or quantum measurements much more resilient to optical losses. So using this scheme, we found that we realized the 4.2 dB squeezing, which is the highest level of squeezing among integrated photonic platform. And also the squeezed light can cover a very wide bandwidth of 25 terahertz. So in addition to signal processing or signal amplification, we also want to use the strong nonlinearity of lithium niobate to tackle the grand challenges in ultrafast information processing. So by using ultra-short pulses, we can even have a terabit per second data rate for communication or computing. But the key challenge of using this technology is that the conventional electronic devices are very slow, so they cannot respond to such a high data rate. So we need some device called the optical switches to process information in terahertz data rate. But realizing this device in solid state platform is very challenging because the optical nonlinearity is usually very weak in conventional materials. So one way that people commonly deal with this challenge is to enhance the nonlinearity by using optical cavities. But this approach widely make the nonlinearity very slow because we dramatically increase the photon storage time in the cavity. And another approach is to leverage the intrinsic material nonlinearity, such as a septal absorption, but this requires a much higher input pulse energy. So the figure of merit of an optical switch is not just the switch in time or energy, but it's actually the energy time product. So the key to make the best optical switch is to leverage materials with a stronger nonlinearity. So this motivates us to construct the best optical switch using our simple lithium niobate. So in your device, we imply a very interesting design. So in the middle of the waveguide, we have a longer physiologic domain called a polling defect, and the defect has a length as long as the polling period. So what it does is that actually flip the phase between the second harmonic and the fundamental by 180 degrees. So as a result, the first half of the waveguide is the second harmonic generation, and the second half of the waveguide is a degenerate OPA, in which the generated second harmonic is serving as a pump to amplify the first harmonic. So based on this idea, here's the design of our optical switch. It contains a main waveguide that can support two different Chi2 nonlinear processes, which are separated by the polling defect. Also, there's a directional coupler next to it. So the directional coupler is wavelength selective. It can linearly couple out most of the first harmonic, but doesn't couple out the second harmonic. So let's see how this device works as an optical switch. So when the input light intensity is small, so it barely generates any second harmonic in the main waveguide. So the coupler can couple most of the input fundamental power out. So if you monitor at the end of the main waveguide, the transmission of the first harmonic will be very low. But if you have a stronger input light pulse, in the first half, we generate a lot of second harmonic, which is shown in the blue. But at the same time, the fundamental wave gets depleted. So in this case, the coupler can only couple out a tiny amount of fundamental power. So in the second half of the waveguide, which is the OPA, the second harmonic will be converted back into the fundamental. So in this case, if you monitor the power at the end of the waveguide, the transmission of the fundamental will be much higher. So we perform the power-dependent transmission measurement using the 2-micron pulse laser. And first of all, in the output coupler, the transmission of 2 micron reduces as we crank the power. Because in the first half, we have a second harmonic generation. So the 2 micron is converting to 1 micron and gets strongly depleted. But if you monitor at the main waveguide, we see that 2 micron transmission increases by more than 5 dB, indicating that OPA is working. So the 2 micron is recovered from the second harmonic. So this nonlinear power-dependent transmission make it possible to use our device to perform optical switching. So we use this setup to measure the dynamics of our switching device. So the 2 micron light pulse are split into one big pulse called the palm and one small pulse called a probe by the microsecond interferometer. And here we send both of them into our devices, and we are trying to use the palm to switch the probe signal on and off. So here we show the switching dynamics of our device by monitoring the power of the probe signal. In the main waveguide, we can use the palm to turn on the probe signal, and in the coupler, we can use the palm to turn off the probe signal. So from the temporal dynamics, we extrapolate that the switching time is only 18 femtosecond. So meaning that our device is fast enough to even respond to pulses as short as 18 femtosecond. So moreover, as can be seen from this plot, the 3 dB switching energy for switching on and switching off operations are 80 femtojoule and 20 femtojoule respectively, which are very low. So we also have demonstrated that extinction ratio per switch is more than 5 dB, which is larger than most of central blower devices. So compared to all the existing optical switches, our device has the fastest switching time, and also our device has the lowest switching time energy product. So now I would like to conclude my talk by showing you how this recent development can point to the future. So in the future, I envision more complex and more functional ultrafast system can be developed by leveraging the thin film lithium niobate and also the strong Chi2 nonlinearity. So as one example, we can leverage the strong interplay between the laser gain and the medium-for parametric gain in the lithium niobate to fill the technology gap of generating femtosecond medium-for pulses on chip. As another direction, we can also think about using the strong optical nonlinearity to fully unleash the potential of photonic computing in terms of high speed, low power consumption, and even higher accuracy. So with that, I'd like to thank you for the attention. I'm ready to take your questions.
All right, thank you for your nice talk. Yiduan?
Thank you, thanks. This was very exciting. So regarding these thin film lithium niobate waveguides that you periodically pull, so what is the impact of the fringing electric field when you're pulling them? How do you take into account those fringing fields and take that into account in the modeling of your periodically pulled Chi2 domains? Can you tell us more about the experiment and modeling of those imperfections, and how do you kind of experimentally validate your modeling and take that into account in the forward model of your waveguides?
Sure, thank you. This is a really great question. So first of all, we apply a very short electrical pulses to push the domain, to flick the domain along the waveguide. So we have to optimize the pulses, the length of pulse, and also the the voltage of each pulse to make the domain perfect. And we found that the trick is that we should have a higher voltage but shorter pulses. In this case, we can get a much better polling quality. And we inspect the polling quality by using the second harmonic microscope. So by looking at by shining light and collecting just the second harmonic, so we can look at the domain after the polling. Okay. And also one comment is that in some experiments, usually we see over polling or under polling. For example, the domains are much wider than we expect, or smaller than 50-50 duty cycle. So this will not change the phase matching condition, but this will reduce the efficiency for the second harmonic generation. So I hope this answers your question. Yeah.
All right, thank you.
All right, any other questions? Yes, Professor Lan Yang.
Hi, Dr. Guo. Thanks. Great to see you online. Great talk. I have a question about your work on femtosecond pulse generation on chip. You chose lithium niobate as a materials platform, but we know it's a very expensive material and it's hard to fab. What is a specific reason to choose these materials? And is there any alternative option in your mind for the future?
Okay. Thank you, Professor Yang. This is a really great question. So the reason we choose this material is that compared to silicon or silicon nitride, which are cheap and more well established, this material provides much higher nonlinearity. For example, if you want to make a femtosecond pulse laser, you need to have a set of absorption or some nonlinear effects that you can generate a solid tone or something more efficiently. But with this Chi2, we can reduce the requirement of high Q optical cavity, and also lower the requirement for the high gain for the generating pulses. So we probably, if you make a central absorber based on this material, we require much lower threshold power. Okay, this is one thing. Another thing is that once you finish making this, on-chip pulse light sources, what can you do with them? So with the lithium niobate, you can use develop the mode-locked lasers or pulse light sources to trigger some other nonlinear effects on lithium niobate, which is much more efficient than Chi3 effects. So this is my answer to your question. Yeah.
Okay, how about the Q factor? Because you use a racetrack resonator for this application. How will the Q factor actually affect the performance of the femtosecond pulse?
Thank you. If you think about Chi3, so probably we need a much higher high Q to ensure there's a large intracavity power to trigger or enable this central absorption of those effects. But for lithium niobate, so we usually make a very low Q cavity in case if the gain is large enough, it can compensate the loss. So then we can already go beyond threshold. And another thing is that probably when people talk about high Q, they think about noise because usually high Q will lower the noise in terms of setup laser. But in terms of making the pulse laser, or we can use the F2F some active locking schemes to lower the noise. So there are many other options other than high Q. Yeah.
Great answer. Thanks a lot.
All right, Professor Drachmir Neshu.
Thank you so much for very nice work and very nice clear talk. So I had a question about the bandwidth of the switch that you presented. So maybe you explained it, but I would just like to ask you to elaborate a little bit more. So what is the bandwidth? Does the QPM limit the bandwidth, and how does the switching time depend on the bandwidth of the QPM?
Thank you. This is a really important question. So ideally, if you ignore all this dispersion mechanism, the bandwidth will ultimately be limited by the QPM. Okay, but here waveguide, although it's dispersion engineered, it still has a tiny amount of dispersion, like the GVD and the GVM. So the GVD will broaden the pulse. So that means, if you have 10 femtoseconds, so probably after the propagation, you get a little bit broadening. And also the GVM, if you have a tiny amount of GVM, so the second harmonic, the fundamental can walk up a little bit. So this will also distort your switching. So currently our device is limited by this dispersion rather than the QPM. Yeah.
Thank you.
All right. Any other last questions? All right. Maybe I'll have a final question for you. So in your last slide, you mentioned about the prospect about using these nonlinearities for optical computing. I remember there was some debate like a decade ago about whether optical computing is a real thing. And how does the power consumption compare with electronic computings, etc. Can you comment on maybe the specifics about your system and maybe the targeted applications you have in mind?
Thank you. So in terms of optical computing, the power consumption usually comes from several factors. First of all, lasers, you have a wall plug efficiency. So laser efficiency is important. Second is that currently most of the existing schemes are utilizing optoelectronic nonlinearity instead of the optical nonlinearity. So if you convert an optic signal into electronics and then convert it back into optics, so you consume another big chunk of the power. So what we are thinking of, our envision is that we do optical computing with ultra short pulses. So each pulse may consume can only have a pulse energy for like hundreds of femtojoule or so, and this energy is enough to even trigger the nonlinear active function. So this is one of my vision. Another thing is that this also means that it's very important to develop very efficient ultra-fast light sources on chip. And this is another thing I think we can improve the efficiency. So in terms of applications, we are pushing for ultra high speed computing schemes, not like megahertz. So we are pushing for 10 gigahertz or even further to make fuse this type of technology or computing architecture with telecom. So this is I think the type of application that I'm thinking of. Yeah.
Okay, great. Thanks for your answer, and thanks for your very nice presentation. I think we are now finished all the presentations from all the speakers. Let's all take a short break of 15 minutes or so. And meanwhile, you will be able to enjoy a very creative movie from the Journal of Life Science and Applications. I hope you enjoyed it. The committees, in the meantime, please send your grades to the organizers so that we can basically come up with the winners today. And after the 15 minutes break, we'll have the ceremony for both the PhD track last week and for the postdoc and faculty track this week. And please don't leave us and join back after 15 minutes. All right. All right, so now we are going to announce the winners of each award. And before we start the ceremony, we would like to invite all the committee members to be back on stage again. And we'll quickly talk with each committee member and have you share with us both the rising stars today in the finalist and the 1,000 more rising stars in the audience, about maybe something you want to say to them or something you want to share about this event. All right, so who wants to start first? Perhaps we start with Albert.
Yeah, I'd love to. So this is, of course, my reaction on today's presentations, because I didn't see them last week for the other award. But I just want to generally say about the 6 that presented today. This was, of course, absolutely top quality research. And it's, I mean, that's no surprise because you've been selected as the best 6 out of a really big group. And I can tell you as jury members, then it's really difficult because you're all very close in our rankings. And so I think we're going to select 3 formal winners, but I hope that the other 3 also will feel themselves winners because you already were in this top quality pool. So with that said, maybe the other thing is that all the topics that we heard today were relatively closely linked also. I was even thinking if the 6 of you would take the initiative to organize a symposium at one of our top conferences, you would all be the 6 speakers also. Maybe that's hard to combine, but that would be a fantastic conference that would attract a lot of people. So I hope also you will find a way to present your work at international conferences because that's what it really deserves. And so what I picked out of it is today is in Lin's talk, very interesting to talk about the future of silicon photonics. I see a really bright future there. I saw Deep's talk on very fundamental aspects of TMDCs, where we'll also see many more things coming out of your lab. And then Chan, impressive new methodologies in this phase imaging and metrology, totally new area. Why again on this amazing Bose-Einstein condensates in perovskites, very tough material to work with, so very impressive too, I thought. And then Yating about integrated silicon photonics, where we really see that the quantum dots have a future to really get gain on a silicon chip. It's something we've been waiting for a long time. And finally, Qiushi, the nonlinear effects on the chip. That's also a totally new area in the way you presented it here. So with that all together, just congratulations to all of you.
Great. Thank you so much, Albert, for your very nice remarks. Professor Lan Yang.
Okay. It's my great honor actually to be part of this wonderful event initiated by Light. As Albert said, it's a really amazing events, including so many wonderful talks. Honestly, it's a very tough job to be a referee for this competition because everyone is incredible, well-accomplished in research, and they are also great speakers. That being said, I think this is a stage for superstar to showcase the impressive research work with great impact to the field of optics, photonics, and beyond. From what I've seen on the screen, actually, there are more than 28,000 people from all around the world watching this. So I would say this is a wonderful opportunity to disseminate our scientific discoveries through this platform. And that being said, thanks for the ICANX platform that initiated by Professor Haisha Zhang and for Chen's leadership for organizing this event. Although we only have one winner, but I would say everyone is amazing. In my eyes, all of you are superstar on this stage. Congratulations to all speakers.
Great. Thank you so much, Professor Yang. Next, maybe Professor Ming Chiu can say something.
Yes, it's really great to hear all the talks, and all these talks are great. And actually, this is my fourth time as a judge for Rising Star Awards by Light. And I think years after years, the event getting better and better. The talks are great, the speakers are great, and it's truly difficult for us to choose and grade the talks. So I would really congratulate these speakers, and I really would like to see more their future works. Congratulations.
Great, thank you so much. And next one, Dragmir Nashib.
Well, I would like to thank first all the participants today. We heard like such an excellent research at the cutting edge of science and technology. And despite it's 2 o'clock in the morning here in Australia, it kept me awake. So fantastic. So we heard so much great science and we learned a lot. So I believe all the audience who listened to us today and the previous competition, previous judgments have learned a lot. And we learn on so many topics and on so many deep science and deep technology. So I just want to say that certainly all the participants today deserve this award today. They can all be the winners. And of course, I congratulate the winners who will probably be a winner just by a very small margin. I congratulate them. And indeed, I second Albert that it will be a great idea to have a conference and do this kind of topic be represented at this conference. Congratulations.
Thank you so much for staying awake at, I assume, 2 a.m. in your morning. And finally, last but not least, Professor Yiduan Ostrang, who is also the chair of this selection committee. Do you have anything to say about our young scientists and the event?
So I think this was a fantastic day with some outstanding presentations. So first of all, congratulations to LSA for initiating this. I think it shows the leadership of the journal in optics and photonics. I'm very excited to actually to hear all the talks today. Everybody deserves, I think, a special recognition for the outstanding work. They were very exciting talks with full energy, and I think they were highlighting the impact of optics and photonics in different ways. Hopefully, something like 30,000 attendees today got the most out of it in terms of understanding the impact of light in our modern society. So congratulations to everybody. the margins of the scores are very small in terms of quality. They're all in the same ballpark. So everybody, I think, is a winner. But at the end, mathematically, we have to select some 3 winners and then spotlight them. But this is actually a day where we spotlight all of the finalists because of their outstanding research. And I think they've done a fantastic job.
All right, great. Thank you again for every committee members for your hard work. And with no further ado, I assume everyone is really eager to know who the winners are. Let's start the ceremony. And I guess I need to take 1 more minute to reiterate the selection process. If you can switch the slide. All right, I guess I'll just directly reiterate the selection process before we officially present the award. The selection process is that basically, as many of you know, in the last week on Friday, we have the 15 minutes presentation followed by Q&A for the PhD candidate track competition. And this week, we enjoyed another 6 talks, again, 15 minutes presentation followed by Q&A from the post-faculty and postdoc track competitions. After all the final winners are selected based on the average grade of all committee members, which are given within 15 minutes after all the talks, excluding members that have a conflict of interest. And we will select 3 winners per track, and each winner will win $1,500 plus an LSA publication fee coupon. And the rest of the 3 also winners, as we heard earlier, from the 6 candidates will win LSA publication fee coupon. All right, so now we start the award ceremony. With no further ado, welcome Professor Ming Chu to present the winner awards for the PhD candidate track.
Yes, it's really a great honor for me to do that. So the winners are Liang Si from MIT and Andrea Cadora from AFM-LF, and Hansen Zhong from University of Science and Technology of China. Congratulations.
All right, congratulations to all the winners. And now, let me welcome Professor Yiduan Ostrong to present the faculty and post-track winners. And these awards are also in honor for Professor Gabriel Popescu. So these are Popescu winner awards. Welcome, Yiduan.
Great. So the Popescu honoring Gabi Popescu and his major contributions to optics, photonics, and in specific computational imaging and holography. This year, LSA and we decided to honor his name as part of the awards. So the Popescu winners of this year will be from Peking University, Dr. Lin Chang. Congratulations for this amazing work and the outstanding presentation today. Congrats. The next winner is Dr. Chao Zuo from Nanjing University of Science and Technology in China. Again, amazing and beautiful presentation with a lot of impact on computational imaging. Congratulations, Chao. And the final winner of the Popescu Award is Dr. Yating Wan from KAUST. And again, a beautiful presentation with a lot of impact on integrated lasers, photonics systems. Congratulations, Dr. Wan. So, and this, of course, also means we congratulate all the finalists for their amazing presentations, outstanding research. That means in the future years, we'll be watching their contributions and their impact on optics and photonics and how they will disseminate their results to young generations. Once again, congratulations to everybody. and thank you again for joining us. And also, I would like to thank the committee members. Some of us were late nighters. Some of us were early morning, early bird. So this is an international effort. So I'd like to also thank my peer committee members from joining us from all around the world. Thank you.
Thank you, Professor Wu Zhang. And I would also like to congratulate for all the winners and all the participants in this award. And I really look forward to seeing new exciting results from each of you in the future. Now, I also would like to thank all the audience for spending 3 hours of time with all of us. And I would like to also thank all the supporters of this event, including ICANX. You are welcome to join future ICANX events every Friday. With that, thank you all. And if you are already Friday evening, have a nice weekend. If you are starting your Friday, enjoy your final day of work in this week, and hope to see you in the next year.